Tonight we're going to examine one of the oldest dreams in human history and one of the most difficult problems the universe has ever placed in front of an intelligent civilization. The dream is simple to describe. Leave Earth, cross the darkness, reach another star, stand beneath an alien sky. It sounds almost inevitable when spoken aloud, as though progress itself guarantees the journey. A species that crossed oceans, climbed mountains, built aircraft, split atoms, and walked on the moon might naturally assume that the stars are simply the next frontier. But there is a dangerous illusion hidden inside that thought. We are descendants of creatures shaped entirely by local distances. We evolved to understand hills, rivers, forests, coastlines, storms, migration routes, and eventually continents. Even our largest achievements still belong to a planetary scale. Our intuition works inside a world where a long journey means days, weeks, perhaps months. Space does not merely challenge that intuition. Space destroys it. Imagine standing outside on a clear night. Thousands of stars scatter across the sky. They feel near in a strange, emotional way. They seem accessible. Ancient civilizations drew stories between them. Sailors navigated by them. Farmers planted according to them. Entire religions were built around them. Human psychology makes a fatal mistake almost immediately. We see brightness and assume proximity. We confuse visibility with reachability. But the night sky is deceptive. The stars do not surround us like lanterns hung just beyond the clouds. They exist at distances so vast that ordinary language begins to fail. The true terror is not that space is empty. The true terror is that almost everything you can see is effectively beyond reach. Consider the nearest star beyond our Sun, Proxima Centauri. It sits just over 4.24 light-years away. At first, that number sounds manageable. 4 years, not so bad. But the phrase light-year hides the real scale. A light-year is not a unit built for human minds. It is the distance light travels in 1 year, moving at approximately 300,000 kilometers every second. In a single second. Light circles Earth more than 7 times. In a single minute, it travels farther than any human has ever physically journeyed. In a year, it crosses nearly 9.46 trillion kilometers. Multiply that by 4.24. That is the distance to the nearest star. Numbers this large create a strange psychological failure. They become abstract. So let us shrink the problem into something physical. Suppose Earth were the size of a marble. The Sun would be a glowing sphere about 15 meters wide, roughly the size of a small house, located over 1.5 kilometers away. Already our solar system becomes much larger than intuition expects. Now place Proxima Centauri into this same model. It would not sit across town. It would not even sit across a country. It would be more than 400,000 kilometers away. On that scale, the nearest star lies farther than the distance between Earth and the Moon, and that is only the nearest star. This is where the story becomes unsettling. Humanity's greatest machines begin to look painfully small. The fastest spacecraft ever launched by humans, Parker Solar Probe, reaches extraordinary speeds by diving close to the Sun. At peak velocity, it moves faster than any object humanity has ever built. Yet if redirected toward Proxima Centauri, even that machine would still require thousands of years to arrive. Not decades, not centuries, thousands of years. Pause there. Thousands of years. Longer than the entire span separating the modern world from the Bronze Age collapse. Longer than the Roman Empire has been gone. Longer than most civilizations survive in recognizable form. Suddenly the question changes. The problem is no longer engineering alone. The problem becomes civilizational. What does travel even mean when the journey exceeds historical memory? What does exploration mean when nobody who begins the mission can possibly witness its end? This is where distance becomes terrifying in a way most people never fully appreciate. Distance in space is not simply measured in kilometers or light years. It is measured in generations, in institutions, in cultural continuity, in biological endurance, in memory itself. Human civilization depends heavily on short feedback loops. A farmer plants crops and harvests within a season. A student studies for years and eventually enters a profession. Engineers build infrastructure, expecting maintenance within decades. Democracies plan around election cycles. Economies operate through rapid exchange. Families transmit stories across perhaps 3 or 4 living generations. Nearly everything human assumes relatively short time horizons. Interstellar distance breaks this assumption completely. Suppose humanity commits to a journey requiring 800 years. The original launch crew becomes history. Their children become history. Entire languages may evolve during transit. Political systems may collapse and re-emerge. Religious beliefs may transform. Social norms may mutate. By arrival, the people stepping onto another world may feel no psychological connection to the civilization that launched them. Then a deeper question appears. If the people who arrive are culturally, biologically, psychologically, and socially different from those who departed, did humanity truly travel to the stars? Or did one civilization die so another could be born elsewhere? This is not philosophy for its own sake. It is embedded directly into the physics of distance. For centuries, humans underestimated this. Early science fiction often treated interstellar travel like ocean voyages. Difficult, yes. Dangerous, certainly. But fundamentally understandable. Build a better ship. Train a better crew. Pack more supplies. Sail farther. But space refuses that analogy. The Atlantic Ocean is vast to a human sailor, yet trivial compared with interstellar voids. The Pacific once felt impossibly large. It now takes hours to cross by aircraft. Even the distance to the moon, which once seemed nearly divine, became a 3-day journey for NASA astronauts. Each time humanity conquered distance on Earth, intuition strengthened. We began believing all distances eventually surrender to technology. Space may be the first domain where that belief fails, because there is another cruel truth hidden beneath the numbers. Distance is not even the real enemy. Not yet. Distance only introduces us to the enemy. The true enemy is time. And once time enters the equation, every comforting assumption about exploration begins to collapse. One obstacle remained. Even if humanity could somehow build a ship fast enough to cross impossible distances leaving Earth, introduces a psychological shift, far more disturbing than simple numbers. Home begins to disappear, and once home becomes unreachable, the journey changes forever. The moment a spacecraft leaves Earth, something profound happens. Long before fuel runs low, long before systems fail, and long before distance becomes measurable in light years, home begins to shrink. At first, the change feels symbolic rather than physical. Cities disappear into continents. Continents fade into oceans and clouds. The borders that consumed politics, war, identity, and history vanish completely. Nations dissolve from view in minutes. Mountains disappear. Rivers vanish. Languages vanish. Economies vanish. From orbit, Earth offers no evidence of the divisions that dominate human civilization. There is only one world, suspended in blackness, carrying every human story ever told. This transformation affected every astronaut who experienced it. During the Apollo 8 mission in 1968, 3 humans traveled farther from Earth than anyone before them. As they rounded the far side of the Moon, Earth disappeared entirely behind lunar rock. For the first time in history, human beings entered a region of space where home was physically absent from sight. Then came the moment that changed space exploration forever. Earth rose above the lunar horizon, blue, white, fragile, silent, a small sphere floating in darkness. The famous Earthrise image became more than a photograph. It became a psychological revelation. Humanity had never truly seen itself before that moment, but even the Moon, for all its symbolic distance, remains close by cosmic standards. Radio signals travelling at light speed take just over 1 second to reach lunar orbit. Mission Control speaks, astronauts answer. Communication remains human, immediate, familiar. Even across nearly 400,000 kilometres, conversation still feels like conversation. That comfort does not last. Imagine a crew travelling outward through the solar system. They pass Mars. Communication delays stretch to minutes. Conversations begin breaking apart. Questions no longer receive instant answers. Decision-making shifts on board. The crew becomes increasingly autonomous because Earth cannot respond quickly enough to guide every action. This is the first subtle fracture between civilization and exploration. Now continue outward. Jupiter, Saturn, Uranus, Neptune. The sun shrinks, its warmth fades, light weakens, solar power becomes unreliable, Earth becomes invisible to the naked eye. Not small, invisible. Pause on that. At some distance, your home world ceases to be a visible object in the universe, not because it is gone, because it is too far away to matter visually. This introduces a terrifying new condition for human psychology. Throughout all of evolutionary history, humans survived through environmental feedback. We saw shelter, we saw threats, we saw family, we saw resources. Vision anchored reality. But deep space strips away these anchors. Outside the spacecraft, there is no weather, no horizon, no birds, no trees, no city noise, no sunrise in the familiar sense. There is only engineered habitat surrounded by lethal vacuum. It turns out distance affects the mind long before it affects the body. Psychologists studying isolation learnt this from submarines, Antarctic research stations, and long-duration orbital missions. Humans tolerate confinement surprisingly well when the environment feels temporary. But once isolation becomes psychologically permanent, something changes. The mind begins to reinterpret time itself. Days lose emotional texture. Routine dominates consciousness. Small conflicts grow disproportionately large. Social dynamics intensify. Memory becomes emotionally loaded. Nostalgia sharpens. Home becomes mythologized. Now scale that to interstellar travel. Suppose you are aboard a vessel leaving the solar system. Earth is already unreachable by rescue. Every supply system, every habitat module, every recycling mechanism matters. Failure becomes absolute. There is no roadside assistance in interstellar space, no emergency landing, no rescue mission, no quick turnaround. Every technical failure becomes existential. This changes human decision-making in ways that civilization has rarely experienced. On Earth, risk is often buffered by redundancy. Hospitals exist, governments intervene, supply chains adapt, communities recover. Interstellar distance destroys redundancy. Self-sufficiency becomes total. A ship crossing deep space is not transportation. It is civilization compressed into metal. That realization leads to a deeper question. How much of civilization must travel with you? At first, the answer seems practical. Food, water, oxygen, medicine, tools, spare parts, power systems, seeds, manufacturing capacity. Simple enough. But then, human reality complicates everything. What about education, law, article, music, religion, conflict resolution, mental health, child development, memory preservation? A spacecraft carrying humans across centuries must contain more than survival systems. It must preserve culture. Not frozen culture, but living culture, capable of adapting without collapsing. And this is where the nightmare hidden inside distance begins to emerge. Distance does not merely separate locations. Distance separates civilizations in time. Imagine sending a message from an interstellar ship halfway to another star. Even at light speed, communication delays become years. A child born on board might send a message to Earth and receive a reply as an adult. Parents may die before responses arrive. Political events become historical artifacts by the time news reaches either side. Conversation ends. Not because communication becomes impossible, because shared time disappears. This may be the first truly devastating consequence of interstellar distance. Civilization depends on synchronization. Markets synchronize prices. Governments synchronize decisions. Science synchronizes discoveries. Families synchronize relationships. Friendship itself depends heavily on shared time. Interstellar distance breaks synchronization permanently. Two human societies, separated by several light years, no longer inhabit the same present. They live in different temporal realities. That sentence sounds abstract until you follow its implications. Suppose Earth discovers a cure for a disease. A colony 12 light years away learns about it 12 years later. Suppose the colony develops a new political philosophy. Earth receives that knowledge 12 years after its creation. Each civilization evolves with permanently delayed awareness of the other. This means something astonishing. Once humanity becomes interstellar, there may no longer be one human civilization. There may be many. Not connected by real-time cooperation, but by slow-moving historical exchange. In other words, the stars do not merely spread humanity across space, they fragment humanity across time. That possibility raises a disturbing question few early dreamers asked. Can humanity remain one species, culturally, politically, or philosophically, when distance prevents shared experience? Or is fragmentation inevitable? The story did not end there, because even this psychological and civilizational challenge assumes one enormous simplification. It assumes travel is possible if we simply accept patience. But there is a brutal physical constraint still waiting beneath everything. A limit so fundamental that every engine, every mission plan, every dream of interstellar travel eventually crashes into it. Humanity can accept waiting. Humanity can endure isolation. Humanity can redesign civilization. But one law appears absolute. Nothing with mass can outrun light. And once that realization enters the story, distance becomes even more terrifying than before. For most of human history, speed meant power. Faster horses changed empires. Faster ships changed trade. Faster communication changed civilization. Then railways compressed continents. Aircraft compressed oceans. Digital networks compressed information itself. Across centuries, progress repeatedly taught humanity the same lesson. Distance shrinks when speed increases. That lesson became so deeply embedded in modern thinking that we rarely question it. Faced with a long journey, our instinct is immediate. Build something faster. Space initially seemed to obey that logic. The first rockets barely escaped Earth. Then came orbital flight. Then lunar missions. Then interplanetary probes. Each generation pushed velocity further. Each breakthrough reinforced optimism. Surely, with enough engineering, enough energy, and enough time, speed would continue rising until the stars surrendered as every frontier before them had surrendered. Then physics intervened. Not as an engineering inconvenience, not as a technological challenge waiting for better materials or larger budgets, as something deeper, a law woven into the architecture of reality itself. In the early 20th century, Albert Einstein formalized a truth that permanently changed humanity's understanding of motion, energy, and causality. The speed of light is not merely fast, it is foundational. Light in vacuum travels at approximately 299,792 kilometers per second, and according to modern physics, this speed behaves not like a recommendation, but like a hard boundary. Information cannot propagate faster. Cause cannot outrun consequence. Reality itself appears structured around this limit. At first glance, this seems abstract, but the consequences for civilization are profound. Suppose you build a spacecraft capable of traveling at 10% of light speed. That achievement alone would represent an engineering revolution beyond anything humanity has ever accomplished. Such a vessel would cross the distance from Earth to the Moon in roughly 13 seconds. It could reach Mars in less than an hour, depending on orbital alignment. The outer planets would cease to feel remote. Jupiter becomes reachable in under 12 hours, Neptune in a matter of days. The entire solar system would psychologically collapse into something closer to a connected archipelago. Humanity would consider this civilization transforming, and yet interstellar travel would still remain agonizingly slow. At 10% of light speed, reaching Proxima Centauri still requires over 40 years, assuming perfect acceleration and deceleration. 40 years to the nearest star. That means the most revolutionary propulsion breakthrough in human history still turns interstellar travel into a life-defining one-way migration. Now consider something more ambitious. Half the speed of light. This sounds almost mythical. A civilization capable of accelerating macroscopic spacecraft to 50% light speed would command energies approaching planetary scales. Entire industrial systems might exist solely to power such launches. Gigantic orbital infrastructure, fusion reactors, beam propulsion networks, civilization-sized energy economies, and even then, the galaxy barely notices. This is the central psychological shock of cosmic distance. Even extraordinary speed feels slow on interstellar scales. The problem becomes clearer when we widen perspective. The Milky Way spans roughly 100,000 light-years across. Light itself, the universal speed limit, requires 100 millennia to cross from one side to the other. That means if a signal left one edge of the galaxy when humans were still painting cave walls, it would not yet have reached the opposite side today. Pause on that. Even light experiences the galaxy as vast. This is difficult for the human mind to accept because our intuition keeps searching for shortcuts. Surely there must be some hidden loophole, some engineering trick, some overlooked mechanism. Humans are remarkably unwilling to accept hard limits. Every historical frontier eventually produced technologies that bypassed earlier constraints. Why should space be different? Because the light barrier introduces something unlike ordinary limitations. Ordinary engineering problems scale with effort. Want a taller building? Use stronger materials. Want faster aircraft? Improve aerodynamics and engines. Want more computing power? Increase architecture efficiency and fabrication density. But relativistic physics punishes ambition non-linearly. The closer an object with mass approaches light speed, the more energy is required to accelerate it further. This is where human intuition collapses. Increasing velocity from 10% to 20% light speed is already demanding. From 80% to 90% becomes vastly harder. From 99% to 99.9% becomes almost absurdly expensive. Each additional fraction of speed demands disproportionately more energy. Reality begins behaving like a wall that grows steeper the faster you climb, and energy itself becomes monstrous. Consider a modest interstellar ship, not a giant city in space, not a generation arc, just a relatively small, crude vessel, perhaps the mass of a modern naval ship. Accelerating such mass to significant fractions of light speed requires energies comparable to the total annual energy consumption of civilizations, not cities, civilizations. Suddenly the question changes again. The challenge is no longer just propulsion, it becomes energy economics. What percentage of planetary industry must humanity dedicate to launching even one starship? Would such missions require global coordination? Orbital megastructures, solar energy harvesting on scales far beyond current civilization. The terrifying truth is emerging. Distance was never just about kilometers. Distance converts directly into energy demand. Energy demand converts into industrial demand. Industrial demand converts into civilizational demand. The ladder keeps climbing. Technology becomes engineering. Engineering becomes economics. Economics becomes politics. Politics becomes civilization. And the deeper we climb, the more unsettling the implications become. Yet there is one subtle detail that makes the story even stranger. From the traveler's perspective, physics offers something extraordinary. Time itself begins to distort. At relativistic speeds, clocks no longer agree. A traveler moving near light speed experiences time differently from observers who remain behind. To someone aboard an ultra-fast spacecraft, the journey may feel shorter than it appears to distant observers on Earth. Years on board could correspond to decades or centuries outside. At first, this sounds like salvation. Perhaps time dilation solves interstellar travel. Perhaps humanity simply rides relativity into the stars. But there is a problem. A devastating one. Time dilation helps travelers. It does not help civilization. Suppose a crew journeys at extreme relativistic speeds and experiences only 10 years on board. Upon arrival, perhaps centuries have passed on Earth. Everyone they knew is gone. Governments have changed, languages may have evolved, entire civilizations may have risen and collapsed. Relativity offers mobility, but it exacts a terrible price. It severs shared history. The explorers arrive alive, yet culturally displaced. They become migrants not only across space, but across time. This leads us toward one of the most disturbing realizations in all of space exploration. The universe may permit interstellar travel, but it may not permit interstellar civilization in the way humans imagine it. Because before we can even confront society, biology, or culture, another problem emerges from the mathematics. The numbers themselves become too large for ordinary thought. Kilometers fail. Miles fail. Even light years begin to feel inadequate. Humanity needs entirely new scales just to describe the distances ahead. And once we start measuring those distances properly, the universe becomes far larger and far more frightening than intuition ever allowed. There comes a point in every exploration where familiar language stops working. Early sailors experienced this when coastlines vanished and the open ocean offered no landmarks. Early astronomers experienced it when telescopes revealed worlds beyond naked eye visibility. Mathematicians experience it when numbers grow so large that symbols remain understandable while meaning disappears. Space forces humanity into all three failures at once. You can still write the numbers, you can still pronounce them, but eventually your mind stops feeling what those numbers represent. That is the hidden danger of cosmic distance. Not ignorance, false familiarity. When someone says the Earth is approximately 150 million kilometers from the Sun, the sentence sounds strangely manageable. 150 million. Large, certainly, but still built from familiar units. Kilometers belong to roads, flights, maps, borders, and commutes. They carry emotional associations. But cosmic scale quietly destroys those associations. The unit survives. Meaning does not. Astronomers learned this early. Ordinary measurements became almost useless once observation extended beyond the solar system. The problem was not mathematical precision, it was human comprehension. Distances grew so quickly that notation itself became hostile to intuition. Millions became billions. Billions became trillions. Scientific notation solved the bookkeeping problem, but not the psychological one. So humanity invented new distance languages. The first major leap was the astronomical unit, or AU, defined using the average distance between Earth and the Sun. 1 AU became a practical solar system ruler. Earth orbits at 1 AU. Mars averages about 1.5 AU. Jupiter sits around 5 AU. Neptune orbits near 30 AU. This helps for a while. The solar system feels organized, measurable, almost elegant. Then something uncomfortable happens. Even the solar system refuses to stay small. Consider the Voyager 1 spacecraft. Launched by NASA in 1977, it became one of humanity's greatest acts of outward motion. It crossed the outer planetary region, sent back historic observations, and continued moving outward decade after decade. Children were born, became adults, had children of their own, and still Voyager 1 kept travelling. Today, after nearly half a century of uninterrupted motion, it remains within the Sun's gravitational domain. It has entered interstellar space in one technical sense, yet it has not remotely escaped the broader influence of our star. That phrase deserves attention. After nearly 50 years of travel, one of humanity's fastest and most enduring machines has barely begun leaving home. This is where intuition begins to fracture. People often imagine the solar system as planets orbiting a sun with empty space beyond. Reality is stranger. The Sun possesses an enormous sphere of influence. Its gravity extends far beyond the visible planetary architecture into distant icy reservoirs such as the hypothetical Oort cloud, a vast region thought to contain trillions of frozen objects. The outer boundary of this cloud may lie tens of thousands to perhaps over 100,000 astronomical units away. Now translate that into more human terms. Light from the Sun takes about 8 minutes to reach Earth. It takes over 4 hours to reach Neptune. It may take nearly 2 years to reach the outermost reaches of the Oort cloud. In other words, the sunlight touching the distant edge of our solar neighbourhood left before many human events that still feel recent. And that is just our local stellar environment. This is why the light year became necessary. Once the solar system expanded beyond practical astronomical unit intuition, astronomers needed a scale matching stellar reality. But even the light year eventually proves insufficient, because stars themselves are not arranged neatly. They form structures within structures, each operating on scales that resist intuition. The Sun belongs to a local stellar neighbourhood containing dozens of nearby stars. That neighbourhood belongs to a spiral arm segment within the Milky Way. The solar system orbits the galactic centre at roughly 220 kilometers per second, which sounds unimaginably fast until another number arrives. One orbit around the galactic centre takes approximately 225 to 250 million years. That means the last time the solar system occupied this exact galactic position, dinosaurs still dominated Earth. Pause there. Your entire species has not completed even one full orbit around the galaxy. Not one. Human civilization is younger still by absurd margins. Agriculture emerged roughly 12,000 years ago. Writing appeared around 5,000 years ago. Industry transformed civilization only a few centuries ago. Spaceflight began less than a century ago. Against galactic timescales, civilization is not young in the ordinary sense. Civilization is almost instantaneous. This creates a profound shift in perspective. Human history feels enormous from inside it. Galactic history renders it microscopic. And the galaxy itself is not remotely the final scale. The Milky Way contains hundreds of billions of stars. Yet it is only one galaxy among perhaps hundreds of billions or even trillions across the observable universe. Between galaxies lie distances so vast that even light spends millions of years in transit. Take our large neighbouring galaxy, Andromeda Galaxy. Light from Andromeda Galaxy requires roughly 2.5 million years to reach Earth. When the photons entering your eyes tonight began their journey, early human ancestors were walking African landscapes, long before civilization, agriculture, language in modern form, or written memory. The light you see is prehistoric, not metaphorically, literally. This realization breaks something deep in human intuition. Looking into space becomes looking into time. Distance and history become inseparable. Every greater distance pushes observation deeper into the past. Stars show delayed presence. Galaxies show ancient histories. The deep universe shows eras before Earth even existed. Suddenly, distance is no longer just spatial separation. Distance becomes temporal separation. The farther outward you look, the less you observe coexistence, and the more you observe archaeological layers of cosmic history. And this creates a paradox at the heart of space exploration. Humanity dreams of reaching distant places, but many of those places are not merely far away. They belong to different historical realities by the time their light reaches us. This is why cosmic distances feel so terrifying. They do more than challenge transportation. They challenge simultaneity. They challenge shared existence. They challenge the assumption that elsewhere means happening now. But there is an even darker consequence hidden inside these scales. Once distance becomes time, a brutal truth emerges. The universe may be navigable in principle, yet human biology operates on a brutally limited clock. And that means the next great obstacle is not space itself. It is lifespan, because eventually every calculation collapses into one unavoidable question. How do fragile beings who live for decades confront journeys that demand centuries? Up to this point, distance has seemed like the central antagonist of our story. Vast emptiness, impossible numbers, the light barrier, interstellar separation. But there is a subtle mistake hidden in that framing. Distance feels terrifying because the human mind visualizes space. We imagine darkness stretching outward. We imagine stars separated by oceans of vacuum. We imagine engines straining against endless emptiness. Yet none of those images capture the true enemy. Distance is only the surface. Time is the force beneath it. This distinction matters because distance in principle can be overcome with speed. Time cannot be negotiated so easily. Time advances with perfect indifference. It does not slow because ambition grows. It does not pause for engineering breakthroughs. It does not care about exploration dreams or civilization. Every second spent travelling is a second irreversibly removed from human life, and human life is short. That sentence sounds obvious, almost trivial, until placed against cosmic scales. The average human lifespan is measured in decades. Even in advanced societies with strong medicine, education, sanitation, and food systems, human lives remain finite and fragile. A child becomes an adult in roughly 2 decades. Middle age arrives quickly. Physical decline begins gradually, then unmistakably. Civilization often speaks in centuries, but biology rarely does. This mismatch between civilizational ambition and biological limitation becomes one of the greatest barriers to interstellar travel, because the moment humanity begins planning journeys to the stars, biology enters the engineering conversation. Consider exploration throughout history. The great terrestrial voyages of the past, however dangerous, usually remained within one lifetime. Ferdinand Magellan launched an expedition that circumnavigated Earth, even though he himself did not survive to complete it. Polar expeditions, transoceanic migrations, and frontier expansion all demanded extraordinary endurance, but participants still expected meaningful progress within years. Even when individuals died, the expedition's timescale remained emotionally human. Interstellar travel breaks this expectation. Suppose humanity builds a ship capable of reaching 5% of light speed, a velocity far beyond anything current civilization can achieve with large crewed vessels. At that speed, a mission to Proxima Centauri requires roughly 85 years, not including acceleration and braking. A child born at launch might arrive near the end of life. A middle-aged crew member almost certainly would not. This is where the problem becomes emotionally real. Interstellar travel may not be exploration in the traditional sense. It may be migration. That distinction changes everything. Exploration implies return report and continuity. A ship departs, gathers knowledge, then reconnects with home. Migration implies departure without return. It implies inheritance rather than mission completion. The travelers do not simply gather information, they transfer civilization. This is an extraordinary psychological burden. Ask a difficult question. Would you board a spacecraft knowing you will never see Earth again? Not just never visit, never even communicate in meaningful, real time. Never walk under familiar skies. Never feel rain on your skin unless simulated. Never smell forests, oceans, soil, or wind, except through memory. Most humans underestimate how deeply environmental familiarity shapes identity. Home is not merely location. Home is sensory architecture, temperature, smell, gravity, soundscape, light cycles, seasonal rhythm, shared culture, collective memory. Remove all of it. Now ask a harsher question. Would you send your children? Because this is where time becomes merciless. Interstellar travel forces moral decisions across generations. The first generation sacrifices certainty for hope. They accept confinement and separation, so descendants may inherit arrival. But those descendants never consented to launch. They are born into mission architecture. Their lives are defined by a destination chosen centuries earlier. This raises profound ethical questions. Can one generation ethically commit unborn generations to a journey they cannot refuse? On Earth, parents constantly shape children's futures. They choose locations, languages, values, opportunities. But interstellar migration amplifies parental influence to civilization-scale magnitude. Future generations may live and die inside engineered environments with no alternative habitat. Suddenly, spacecraft design becomes social design. Habitat volume influences mental health. Population size influences genetic diversity. Education systems influence cultural stability. Governance structures influence conflict resolution. Every engineering decision becomes a civilizational decision, and time continues moving. Biology introduces another complication. Human bodies are not designed for indefinite space habitation. Even in low Earth orbit, astronauts experience muscle loss, bone density reduction, fluid redistribution, immune changes, and subtle neurological effects. NASA and other space agencies have spent decades studying long-duration spaceflight because even months away from Earth produce measurable physiological stress. Now scale from months to decades, or centuries. A multi-generational interstellar mission must solve not only propulsion and life support, but biological continuity. Pregnancy, childbirth, childhood development, aging, disease management, surgery, mental illness, injury, and elder care all become closed-loop problems. There is no hospital down the road, no external pharmaceutical supply, no emergency evacuation. Civilization becomes fully self-contained. This is where a disturbing realization emerges. Interstellar ships cannot merely carry humans. They must carry human systems. Medicine, manufacturing, agriculture, education, governance, justice, culture, ritual, meaning. Because time erodes more than bodies. It erodes purpose. And purpose may be the most fragile resource on board. Imagine the third or fourth generation aboard a starship. The original launch may have been historic, monumental, sacred. But memory fades. Myth replaces direct experience. Children born centuries into transit may not emotionally identify with Earth at all. The mission may feel abstract, ritualized, burdensome. Why continue obeying ancestors long dead? Why maintain destination loyalty? Why preserve mission discipline? This is not a trivial concern. History shows civilizations repeatedly struggle to maintain coherent purpose across long timescales. Empires fragment, institutions decay, founding ideals mutate. Even stable societies experience ideological drift within generations. Time changes everything, including intention. That is why time is more terrifying than distance. Distance separates places. Time separates values. And values determine whether civilization survives. But there is another layer to the problem, one even engineers sometimes underestimate. Humans assume longer journeys simply require more supplies. That logic works on Earth. Bring more food, more fuel, more equipment. In space, that intuition creates a devastating trap, because every additional resource increases mass, and mass changes propulsion, which means solving time by going faster introduces another crisis entirely. the story did not end with biology. It returned to physics, and waiting ahead was one of the cruelest equations humanity has ever confronted. The faster you want to travel, the heavier your ship becomes. And the heavier your ship becomes, the more impossible acceleration starts to feel. This is where countless dreams of reaching the stars begin to collapse, because time may be the enemy, but fuel is the prison. For centuries, propulsion seemed like the obvious solution. If distance is too large and time is too short, build faster engines. That instinct feels so natural that it shaped nearly every early vision of interstellar travel. Engineers imagined larger rockets, more efficient fuel, stronger materials, and more powerful thrust. Each new generation of propulsion technology seemed to promise the same thing: more speed, less travel time, and eventually, access to the stars. But there was a problem. Rocket engineering contains a hidden cruelty that punishes optimism. Every spacecraft carries a simple burden. To move, it must push mass in the opposite direction. On Earth, vehicles exploit external systems. Cars push against roads. Aircraft push against air. Ships push against water. Rockets are different. In space, there is nothing to push against. A rocket must carry both the vehicle and the reaction mass it throws away to generate thrust. This sounds manageable until the numbers become severe. Suppose you want to double mission velocity. Intuition suggests doubling engine performance or doubling fuel. Reality is harsher. Because fuel itself has mass, adding more fuel increases the mass that must be accelerated. That additional mass then requires more fuel to accelerate. That added fuel adds still more mass, demanding still more fuel. The logic spirals. It is a feedback loop so unforgiving that it became one of the central constraints of astronautics. In the late 19th century, long before humans reached orbit, Konstantin Tsiolkovsky recognized this with extraordinary clarity. Working in Kaluga, he derived the mathematical relationship governing rocket motion. His equation revealed a truth both elegant and brutal. Rocket performance depends exponentially on mass ratio. Small gains in required velocity can demand enormous increases in propellant. This changed the dream of interstellar travel. Suddenly, the challenge was not merely building better engines, it was escaping exponential punishment. To understand how severe this becomes, imagine a spacecraft designed for deep space travel using conventional chemical propulsion, the same broad principle that powered the Apollo program. Chemical rockets are extraordinary machines. They enabled humanity's first great leap beyond Earth. But on interstellar scales, they become painfully inadequate. A chemical rocket capable of reaching another star within a human lifetime would require absurd fuel fractions. Depending on mission assumptions, nearly the entire launch mass would need to be propellant. Payload shrinks toward irrelevance. Habitat volume disappears. Shielding becomes impossible. Crew survival becomes fantasy. In simple terms, a conventional rocket becomes mostly fuel designed to accelerate more fuel. The ship almost vanishes. Engineers quickly realized that chemical propulsion would not open the stars, so humanity searched for better engines. Ion propulsion emerged as one promising alternative. Unlike chemical rockets, ion engines generate relatively low thrust, but achieve remarkable efficiency by accelerating charged particles to high speeds. This makes them ideal for long-duration robotic missions. Dawn demonstrated the power of this approach, travelling vast distances while consuming far less propellant than traditional rockets. At first, ion propulsion seems like a breakthrough. Higher efficiency means less fuel. Less fuel means lower mass. Lower mass means easier acceleration. The logic appears promising, but space introduces another trap. High efficiency often comes at the cost of low thrust. Ion engines are patient engines. They accelerate gently over long durations. That works beautifully for lightweight robotic probes. Humans are different. Crewed interstellar missions need massive habitat systems, radiation shielding, life support redundancy, agricultural infrastructure, and structural integrity. The mass rises dramatically. Suddenly, the gentle push of ion propulsion becomes insufficient for practical crew acceleration. Faster engines help, but not enough. The equation remains merciless. Then came nuclear propulsion. The idea felt revolutionary, because nuclear reactions release vastly more energy per unit mass than chemical combustion. The energy density difference is so large that early theorists believed atomic propulsion might finally break humanity out of the rocket trap. If chemical fuel could not reach the stars, perhaps the atom could. This optimism intensified during the mid-20th century. The atomic age transformed human imagination. Nuclear power promised not just weapons or electricity, but access to entirely new scales of energy. For the first time, interstellar travel felt less like fantasy and more like engineering. But the story did not resolve there, because increasing energy density solves only part of the problem. A propulsion system needs more than raw energy. It needs usable momentum transfer. It needs thermal management. It needs shielding. It needs structural resilience. And above all, it must keep humans alive. Each improvement uncovered deeper complexity. Consider acceleration itself. Humans often focus on maximum speed, but velocity is only half the journey. A spacecraft must accelerate outward, then eventually slow down. Reaching another star at extraordinary speed is useless if arrival becomes impact. Deceleration requires energy comparable to acceleration. This doubles the challenge. You do not just need enough propulsion to leave, you need enough propulsion to stop. That single fact destroyed many optimistic designs. A ship capable of incredible acceleration may still carry insufficient energy reserves for controlled arrival. The result is not exploration. It is flyby extinction. Then another obstacle appeared: waste heat. This problem receives far less public attention, yet it may be among the most dangerous. Engines converting enormous energy inevitably generate heat. On Earth, atmosphere and convection help remove thermal buildup. In vacuum, heat dissipation becomes much harder. Spacecraft rely heavily on radiators. As energy scales upward, radiator requirements become enormous. This creates a strange engineering paradox. More powerful engines may demand larger thermal systems. Larger thermal systems increase mass. Higher mass demands more propulsion. Again, the trap closes. The deeper engineers explored propulsion, the clearer the pattern became. Every apparent solution carried a hidden penalty. More speed required more energy. More energy required more infrastructure. More infrastructure required more mass. More mass required more fuel. Every path curved back toward the same wall. This is why the dream of faster rockets began changing in character. Early visions imagined single, heroic vehicles crossing the stars. Modern thinking became more cautious. Perhaps the ship itself was the wrong unit of analysis. Perhaps propulsion should not rely solely on onboard energy. Perhaps the engine should not travel with the spacecraft at all. That idea would later become important. But before humanity reached that insight, a far more radical dream captured scientific imagination. If rockets were trapped by fuel, perhaps civilization needed a propulsion source so powerful it could overwhelm the equation entirely. Not stronger chemistry. Not incremental efficiency. Something far more extreme. The atom had opened one door. Now scientists wondered whether controlled nuclear power could push humanity into an entirely new age of spaceflight. For a moment, it seemed possible. For a moment, the stars looked closer. Then the engineering reality arrived. And with it came one of the boldest and strangest propulsion proposals ever seriously designed. By the middle of the 20th century, the optimism surrounding atomic energy had reached extraordinary levels. Nuclear physics had revealed forces hidden deep inside matter, energies so concentrated that even small quantities of fuel could unleash civilization-altering power. To engineers dreaming of interstellar travel, this felt like the long-awaited escape from the tyranny of conventional rocketry. Chemical fuel had failed. Efficiency improvements had helped, but not solved the core problem. Perhaps the atom could do what combustion never could. At first, the numbers looked promising. Chemical reactions rearrange electrons. Nuclear reactions alter atomic nuclei. The difference in available energy is immense. If a spacecraft could exploit that energy safely and efficiently, then perhaps the crushing mass penalties of conventional rockets could finally be reduced. Travel times might shrink from millennia to decades. The stars for the first time began to feel faintly accessible. Then the deeper arithmetic arrived, and the optimism began to fracture. The central problem was not merely energy density. Humanity had slowly learned that raw energy alone does not guarantee useful propulsion. A spacecraft must convert stored energy into directed momentum. It must accelerate mass backward to move forward. That mass can be chemical, exhaust, ionized particles, plasma, or something more exotic. But no matter the method, propulsion remains tied to momentum exchange. This is where the fuel catastrophe revealed itself. Even with nuclear power, a ship still faces a brutal accounting problem. Energy can become vastly more abundant, but unless propulsion efficiency approaches extraordinary levels, propellant requirements remain enormous. Worse, crewed missions demand shielding, habitat volume, redundancy, repair capability, food systems, medical systems, and long-term reliability. Every survival feature adds mass. Every kilogram must be accelerated, and accelerated mass is expensive. Imagine building a starship the size of a modern city block. Not a giant orbital megastructure, just a modest crewed interstellar vehicle with life support, radiation protection, storage, structural reinforcement, and habitat modules. Now imagine accelerating it to a meaningful fraction of light speed. The energy required becomes staggering, not merely large, civilization scale. This is the point where interstellar engineering stops feeling like engineering and starts feeling like economics. How much industry must humanity dedicate to a single launch? How much planetary energy must be diverted? How many power plants, orbital factories, refineries, launch systems, and mining networks must exist before one starship becomes practical? The numbers quickly became uncomfortable. Then came one of the boldest proposals in the history of spaceflight. In the late 1950s and early 1960s, engineers working on Project Orion proposed something so radical that even today it feels almost surreal. Instead of relying on continuous fuel burn, the spacecraft would detonate a sequence of small nuclear explosives behind itself. Each explosion would strike a massive pusher plate, transferring momentum forward. Explosion after explosion, pulse after pulse. The vehicle would accelerate through repeated controlled detonations. It sounds absurd, but it was real engineering, and it was taken seriously. Among those associated with Orion was Freeman Dyson, one of the most imaginative scientific minds of the 20th century. Dyson understood that interstellar travel demanded thinking beyond incremental improvements. Orion was not elegant, it was violent, industrial, almost primitive in spirit. Yet its raw physics had undeniable appeal. Instead of fighting fuel limitations with small efficiencies, Orion attempted brute force, used nuclear explosions as propulsion, mountain-sized energy delivered in pulses. The proposed ships were enormous. Some designs envisioned vehicles weighing thousands or even millions of tons. These were not rockets in the traditional sense. They were moving infrastructure, flying civilizations in early form. For a moment, it seemed humanity had found a path. Project Orion calculations suggested velocities far beyond chemical rockets. Missions to the outer solar system could be dramatically shortened. Some speculative versions even hinted at interstellar precursor missions. Then the complications arrived. First came politics. Detonating hundreds or thousands of nuclear devices as propulsion created obvious geopolitical problems. The Cold War had already made atomic weapons existentially terrifying. Launching nuclear pulse ships from Earth introduced fallout contamination, treaty conflicts, and strategic instability. Even if technically feasible, Orion collided with planetary politics. But politics was not the deepest flaw. Engineering was. Repeated nuclear detonations impose extraordinary mechanical stress. The pusher plate must survive thermal shock, radiation exposure, and repeated high-energy impacts. Shock absorbers must smooth explosive impulses into survivable acceleration for crew and structure. Material fatigue becomes severe. Maintenance becomes critical. Reliability becomes existential. Then came another problem: radiation. Deep space already exposes travelers to cosmic rays and energetic particles. Nuclear propulsion adds another layer of radiation hazard. Shielding improves safety, but increases mass. Increased mass requires more propulsion. Again, the equation tightens. And then the cruelest realization emerged. Even Orion-like systems, revolutionary as they were, still did not truly solve interstellar civilization. They improved speed. They did not eliminate time. This distinction became devastating. Suppose a nuclear pulse starship reaches several % of light speed. Remarkable. Historic. Civilization transforming. Yet the nearest stars still remain decades away. More distant targets remain centuries away. The galaxy remains effectively unreachable within human lifetimes. The fuel catastrophe had evolved. It was no longer simply about propellant mass. It was about scaling ambition. Every improvement helped locally, while failing cosmically. This is what makes space so psychologically punishing. Progress can be genuine and still insufficient. Humanity kept climbing technological ladders. only to discover that the universe had built a taller wall behind each rung. Chemical rockets failed. Advanced electric propulsion helped, but remained too weak. Nuclear propulsion expanded possibilities, but still left enormous gaps. Every breakthrough produced hope. Every hope revealed deeper limits. And yet, something subtle had changed. Scientists began recognizing that propulsion alone might never fully solve the problem. Faster engines could shorten travel time, but not enough. At some point, another question became unavoidable. What if the real constraint was not the ship? What if the real constraint was the passenger? This shift changed the entire conversation. For decades, engineers had asked, how do we move humans farther and faster? Now a more unsettling question emerged. Can humans survive what the journey demands? Because even if propulsion becomes possible, interstellar travel confronts a threat far more intimate than fuel equations. Radiation enters the body. Isolation enters the mind. Microgravity reshapes biology. Closed environments stress social systems. And unlike fuel, these problems cannot simply be solved by adding more mass. The story did not end with engines. It turned inward. From reactors and propulsion plates to flesh-bone neurons, memory and psychology. The next obstacle was not mechanical. It was human. Because reaching the stars may demand something far more difficult than building a ship. It may demand surviving the journey without losing the very biology that made the journey meaningful. Once humanity understood that chemical propulsion would never carry large crews to the stars, nuclear energy became more than a promising alternative. It became a psychological refuge. Engineers, physicists, and futurists needed something powerful enough to preserve hope. The stars had grown more distant with every honest calculation. Nuclear physics offered a rare counterforce. It suggested that nature itself contained energy reserves vast enough to challenge cosmic scale. For a time, that idea changed the mood of interstellar thinking. The question shifted from whether the stars were reachable to what kind of nuclear civilization would be required to reach them. This distinction mattered. A civilization that merely uses nuclear reactors for electricity is very different from a civilization that reorganizes its industry infrastructure and long-term planning around nuclear-powered expansion into space. Suddenly, interstellar travel was no longer just about spacecraft design. It became a planetary development question. What kind of civilization must humanity become before the stars become realistic? This question drove some of the most ambitious engineering studies ever attempted. In the 1970s, the British Interplanetary Society undertook one of the most remarkable conceptual projects in spaceflight history, Project Daedalus. Unlike earlier speculative visions, Daedalus aimed to produce a serious engineering blueprint for an unmanned interstellar probe. The target was Barnard's Star, located roughly 6 light-years from Earth. The design was staggering. Daedalus would not resemble a traditional spacecraft. It would be a machine of industrial proportions. The proposed vehicle mass exceeded 50,000 tons. Most of that mass would be fuel. Its propulsion system relied on inertial confinement fusion, repeatedly igniting tiny fuel pellets using electron beams to generate controlled fusion explosions. This was not conventional engineering scaled upward. It was civilization-scale engineering. Picture the vehicle, an immense skeletal structure floating in deep space. Fuel tanks the size of buildings. Massive engine assemblies designed to withstand repeated fusion pulses. Radiators stretching outward. Guidance systems operating for decades without human maintenance. A machine less like an aircraft and more like an autonomous industrial organism. For the first time, the numbers became astonishing in a new direction. Daedalus calculations suggested cruise speeds approaching 12% of light speed. 12%. That number electrified interstellar researchers. At that velocity, a probe could reach its target in roughly 50 years. 50 years. Not centuries. Not millennia. Half a human lifetime. For the first time, a star mission seemed to move from fantasy into theoretical engineering. But there was a problem. Several, in fact. The first was fuel acquisition. Fusion sounds elegant because of its immense energy density. Fuse light nuclei and release extraordinary energy. In theory, it offers one of the most powerful energy sources available to civilization. In practice, controlled fusion remains among the hardest engineering challenges humanity has ever pursued. Even today, after decades of research, practical large-scale fusion power remains elusive. Building a stable fusion reactor on Earth is already difficult. Building one robust enough to repeatedly drive interstellar propulsion introduces another level of complexity entirely. Then came fuel sourcing. Daedalus proposed using helium-3 and deuterium isotopes, attractive for fusion reactions. But helium-3 is rare on Earth. Meaningful quantities would likely require large-scale extraction from gas giants, such as Jupiter, or from extraterrestrial industrial networks not yet built. Pause on that implication. Before launching one interstellar probe, humanity might need a mature space-based industrial civilization, not to explore the stars, just to prepare. That realization changed the psychological scale of the challenge. Interstellar travel was no longer a mission. It was the byproduct of becoming a different civilization. And then came reliability. This problem haunted every nuclear dream. A fusion-powered interstellar craft traveling for decades cannot rely on maintenance crews, repair docks, resupply chains, or replacement hardware. It must survive extreme vibration, thermal cycling, radiation exposure, micrometeoroid impacts, software degradation, and hardware aging for generations of machine time. A single failure in a critical subsystem may end the mission permanently. Redundancy helps, but redundancy increases mass. Mass increases fuel demand. Again, the trap returned. Then engineers encountered another cruel reality. Interstellar space is not empty in the comforting sense people imagine. Yes, matter density is extremely low, but at relativistic speeds, even tiny particles become dangerous. Dust grains, gas atoms, and microscopic debris transform into high-energy impact hazards. A small particle striking a ship moving at significant fractions of light speed can deliver extraordinary destructive energy. This created a frightening image. The faster humanity travels, the more dangerous space becomes. Speed does not merely reduce travel time, it amplifies collision energy. Suddenly, the universe gains teeth. A single grain of dust can become a weapon. Shielding helps, but shielding increases mass. Mass demands more energy. The pattern had become almost cruelly familiar. Every breakthrough came attached to a hidden cost. Project Daedalus proved something important. Physics did not strictly forbid meaningful interstellar missions. That was enormous. The universe had not closed the door completely, but the cost of opening that door appeared extraordinary. Fusion dreams gradually evolved into something more philosophical. Engineers began asking a difficult question. Suppose humanity solves propulsion. Suppose fusion works. Suppose fuel sourcing works. Suppose shielding works. Suppose guidance systems work. What exactly arrives at the destination? A machine, a probe, a civilization, a human crew. This question mattered because nuclear propulsion primarily addressed energy and speed. It did not solve the most fragile system in any starship: human biology. And biology is unforgiving. Cells accumulate damage. Radiation mutates DNA. Muscles weaken. Bones lose density. Immune systems adapt unpredictably. Brains respond to isolation in complex ways. In other words, even if nuclear engineering succeeds, biology may still fail. This realization marked a turning point in interstellar thinking. The challenge was no longer dominated by engines. It began shifting toward life support at the deepest possible level, not oxygen generators, not food recyclers, life itself. Can human biology remain stable across decades or centuries of artificial existence? Or does the journey slowly transform the traveller into something else? Because the deeper scientists looked into long-duration space habitation, the clearer one uncomfortable truth became: the greatest threat to a starship may not come from outside. It may come from the passengers within. And that led humanity into a problem far stranger than fuel propulsion or fusion, a problem written directly into muscle, blood, bone, and mind. By now, the shape of the problem had changed completely. At the beginning of our journey, interstellar travel looked like an engineering challenge. Build stronger engines, generate more energy, accelerate faster. But the deeper humanity looked, the more unsettling the truth became. Machines were only part of the equation. Even if propulsion reached extraordinary levels, even if energy became abundant, even if starships became technically feasible, one system remained dangerously fragile: the human body. This fragility is easy to overlook because life on Earth feels robust. Humans adapt to deserts, mountains, polar winters, tropical humidity, high altitude, deep oceans, and dense cities. We survive through intelligence and technology. That adaptability creates confidence. It encourages a quiet assumption that humans can live almost anywhere if given sufficient tools. Space dismantles that confidence. Because Earth does not merely provide resources, Earth actively protects biology every second. Its gravity shapes bone growth, muscle maintenance, circulation, posture, and organ orientation. Its magnetic field shields life from charged particles. Its atmosphere absorbs radiation and moderates temperature extremes. Its biosphere supplies oxygen, food, microbial diversity, and ecological stability. Most humans rarely notice these protections because they are constant. Remove them, and biology begins changing immediately. Long-duration orbital missions revealed this with disturbing clarity. Astronauts aboard International Space Station became participants in one of the most important biological experiments in history. In microgravity, muscles atrophy because the body no longer works against weight. Bones lose mineral density because skeletal loading decreases. Fluids redistribute upward, affecting facial appearance, intracranial pressure, and even vision. Cardiovascular systems adapt to weightlessness, often making readjustment to gravity difficult. These effects appear within months, not decades, months. That timeline matters. A Mars mission already pushes human biology toward uncomfortable limits. Interstellar travel expands those limits into largely unknown territory. Consider the simplest question. What happens to a child conceived and born in space? No human knows. That uncertainty alone reveals how early humanity remains in spacefaring biology. Pregnancy is not merely growth inside a womb. It depends on complex biomechanical signals involving circulation, fluid balance, tissue stress, hormonal timing, and developmental regulation. Gravity influences posture, skeletal loading, vestibular function, and spatial orientation during development. Remove gravity entirely, and the consequences become deeply uncertain. Would embryonic development proceed normally? Would skeletal growth weaken? Would balance systems mature properly? Would birth itself become more dangerous? Interstellar civilization cannot avoid these questions. If missions exceed human lifetimes, reproduction becomes unavoidable. The moment children are born on board, Starship design ceases to be transportation. It becomes habitat ecology. This realization created a profound shift in thinking. Engineers once focused on engines and hulls. Now, they had to think like ecologists. A human being is not an isolated machine. Each person carries vast biological complexity. Trillions of human cells coexist with microbial ecosystems that influence digestion, immunity, metabolism, and mental health. A closed, artificial habitat must preserve not only humans, but the biological networks humans depend upon. This introduces one of the least intuitive challenges in long-duration space travel: microbial collapse. On Earth, microbial exchange occurs constantly. Soil, air, plants, animals, water, food, and other humans continuously shape biological ecosystems. In closed environments, microbial diversity can narrow dangerously. Some species disappear, others dominate. Harmful strains may evolve. Biofilms form in machinery. Contamination becomes systemic. In short, life support means supporting more than human life. It means supporting entire living systems. Then comes radiation. This may be the most relentless biological threat in deep space. Low Earth orbit still benefits from partial shielding by Earth's magnetic environment. Beyond that protection, exposure rises dramatically. Galactic cosmic rays, solar energetic particles, and other high-energy radiation sources bombard deep space continuously. Unlike ordinary environmental hazards, radiation can pass through tissue, damaging DNA, increasing cancer risk, degrading cells, and potentially affecting neurological function. Radiation shielding sounds straightforward. Use thicker walls. Add protective mass. But here the familiar trap returns. Shielding requires mass. Mass requires propulsion. Propulsion requires energy. Every biological solution re-enters the engineering equation. The deeper humanity looked, the more interconnected the problem became. Biology could not be separated from physics. Then researchers uncovered something even more troubling. Space may affect the brain in subtle but serious ways. This goes beyond loneliness or boredom. Human cognition evolved inside rich sensory environments. Forests rustle. Cities hum, weather changes, smells shift. Gravity constantly informs the vestibular system. Circadian rhythms synchronize with natural light cycles. The brain expects complexity. Deep space offers the opposite. Artificial lighting, engine noise, controlled airflow, recycled atmosphere, limited scenery, constrained social circles, predictable routines. Monotony becomes structural. This matters because psychological health depends partly on environmental richness. In isolation, studies across Antarctic bases, submarines, and simulated Mars habitats, researchers repeatedly observed familiar patterns: sleep disruption, irritability, reduced motivation, social tension, emotional withdrawal, cognitive fatigue. Minor conflicts gained disproportionate emotional intensity. Now imagine, not months, years, decades, generations. Psychology becomes infrastructure. A starship cannot merely keep bodies alive, it must keep minds coherent. This leads to a startling realization. Entertainment becomes survival. Art becomes survival. Ritual becomes survival. Beauty becomes survival. Why? Because meaning protects mental stability. A civilization stripped of novelty and emotional richness risks psychological stagnation. Children need play. Adults need aspiration. Communities need celebration. Grief processing, symbolic identity and shared purpose. Remove these, and social cohesion erodes. This may be the most profound lesson of interstellar biology. Humans do not survive on oxygen alone. They survive on meaning. That sentence sounds philosophical, but for long-duration space travel, it becomes operationally practical. Meaning affects compliance. Compliance affects cooperation. Cooperation affects survival. And yet, even if humanity solves biology, radiation, ecology, and psychology, one obstacle remains larger than the individual. A starship is not inhabited by one body, or even one family. It contains a society, and societies introduce something no propulsion model can fully predict: conflict, power, hierarchy, trust, law. The problem had escalated again, from engines to bodies, from bodies to minds, now from minds to civilization. Because a vessel traveling for centuries cannot depend solely on individual resilience, it must survive collective human behavior. And history offers a difficult warning. Human societies rarely remain stable for long without institutions strong enough to outlast generations. That is where the next great challenge emerged. Not technological, not biological, civilizational, because the hardest question was no longer whether humans could survive deep space physically. It was whether a society could survive deep time without collapsing from within. By this point, the nature of the challenge had transformed beyond recognition. What began as a question about propulsion had become a question about survival. Then biology complicated survival. Psychology complicated biology. Now the final escalation emerged, perhaps the most difficult of all. Civilization itself had become the spacecraft's most fragile system. This realization marked a profound turning point in how serious thinkers approached interstellar travel. For decades, popular imagination focused on ships, engines, reactors, and navigation systems. These are visible technologies. They are easier to imagine because they obey engineering logic. A machine breaks, you repair it. A component fails, you replace it. Engineering problems, however difficult, often feel tractable. Civilizations do not behave like machines. They are dynamic systems built from trust, power, culture, memory, law, economics, identity, and belief. They evolve unpredictably. They fragment. They adapt. They produce cooperation and conflict simultaneously. Most importantly, they rarely remain unchanged across generations, and interstellar travel may require many generations. That single fact changes everything. Imagine a generation ship carrying 10,000 people toward a star system 200 years away. The launch itself would be one of the greatest events in human history. Entire nations might contribute resources. Architects, engineers, ecologists, physicians, educators, and political leaders might spend decades preparing the mission. Ceremonies would mark departure. Promises would be made. Foundational charters would be written. The first generation would understand the mission intimately. They chose it. They accepted its costs. But the second generation did not choose launch. They inherited it. The third generation inherited even less direct connection. By the fifth or sixth generation, something historically familiar begins to happen. Founding purpose weakens. This pattern appears repeatedly across civilizations on Earth. Revolutions begin with intense ideological commitment, then soften as memory becomes institutional rather than personal. Religions emerge through direct, charismatic influence, then transform through ritual and doctrine. Empires expand through strategic necessity, then drift into bureaucratic complexity. Founders act with urgency. Descendants often inherit systems without inheriting the emotional force that created them. A starship would not escape this pattern. In fact, distance may amplify it. Consider law. How should a generation ship govern itself? At first glance, democratic governance feels appealing. Shared participation encourages legitimacy. But democracy assumes informed citizens, communication systems, civic norms, and stable institutional trust. Long-duration closed environments may stress these assumptions. Resource scarcity, emergencies, and system failures can pressure societies towards centralized authority. Now consider authoritarian control. A strict command structure may preserve order during crisis, but over centuries, concentrated power risks abuse, corruption, repression, or dynastic capture. Historical precedent offers little comfort. Centralized authority often stabilizes systems temporarily, while increasing long-term fragility. Neither model guarantees success. Then comes economics. Earth-based economies rely on expansion, trade, specialization, and external resource flows. A starship has no external market, no imports, no exports, no frontier for extraction. It is a closed economic ecosystem. This creates extraordinary pressure. Waste becomes existential. Overconsumption becomes dangerous. Inequality becomes volatile. Suppose a small elite gains disproportionate access to habitat space, luxury resources, or decision-making power. Resentment grows. Social trust erodes. Conflict intensifies. In terrestrial societies, migration sometimes relieves tension. Dissatisfied populations relocate. A starship offers no frontier. There is nowhere to leave. Closed environments magnify conflict, and conflict introduces the darkest civilizational question: violence. Human history is filled with cooperation, creativity, and moral growth. It is also filled with war, tribalism, ideological conflict, and power struggle. Interstellar idealism often imagines that only highly enlightened societies would attempt generation travel. History suggests caution. Technological sophistication does not eliminate human conflict. Advanced societies still compete, still polarize, still fracture. Now imagine conflict aboard a closed starship. A civil war on Earth is catastrophic. A civil war inside a sealed interstellar habitat may be terminal. Damage to life support systems, agriculture modules, water recycling infrastructure, or power systems could kill thousands rapidly. Violence becomes more dangerous because civilization lacks environmental redundancy. Peace stops being ethical preference. Peace becomes engineering necessity. This is where governance evolves into something deeper. Conflict resolution becomes survival infrastructure. Justice becomes survival infrastructure. Education becomes survival infrastructure. Even cultural storytelling becomes survival infrastructure. Why storytelling? Because stories preserve collective purpose. Humans do not maintain civilization through rules alone. They maintain it through narratives explaining why sacrifice matters. Foundational myths, shared memory, ritual, and identity bind generations across time. A starship civilization would need stories powerful enough to survive centuries. Children born on board must believe the mission matters, not abstractly, emotionally. They must understand why discipline matters, why maintenance matters, why cooperation matters, why arrival matters. Without narrative continuity, mission continuity collapses. This raises a haunting possibility. Over centuries, the ship itself may become home, not temporary habitat. Home. That distinction matters enormously. The original mission assumes destination loyalty, but descendants may reject that assumption entirely. If generations live, love, build culture, raise children, and bury ancestors aboard the ship, why assume arrival remains desirable? The vessel may no longer feel like transport. It may feel like civilization. This possibility deeply unsettled futurists. A generation ship may succeed technically, while failing philosophically. The passengers may simply stop wanting arrival. Pause on that. Humanity could build a starship capable of reaching another world, only for the civilization on board to decide not to land. This is not absurd. History shows communities repeatedly redefine purpose when circumstances change. Migration goals transform, Ideologies adapt. Survival reshapes values. The deeper thinkers examined generation travel, the clearer one truth became. Interstellar civilization is not just about crossing distance, it is about preserving intention. And intention is fragile. So fragile, in fact, that many scientists began questioning whether generation ships were truly the best path at all. What if the problem was not only speed? What if the deeper issue was human continuity? What if, instead of asking how civilization survives centuries of travel, humanity asked a more radical question? Could we avoid the long journey altogether? This question changed the direction of interstellar thought. After decades of wrestling with engines, fuel biology, and civilizational drift, a new generation of thinkers emerged. They did not begin with rockets, they began with physics itself. And among them stood one of the most important dreamers in the history of space exploration, a school teacher in Russia, working in relative obscurity, writing equations that would launch humanity toward the stars while quietly revealing the scale of the challenge ahead. His name was Konstantin Tsiolkovsky, and his vision would reshape everything. Long before rockets pierced the upper atmosphere, before satellites orbited Earth, before astronauts looked back at our planet from the moon, one man sitting in provincial Russia began thinking seriously about humanity's future in space. He had no launch pad, no aerospace industry, no computers, no government program funding interplanetary research. He worked largely in isolation in a world where powered flight itself was still new. Yet he saw farther than most of his era. Konstantin Tsiolkovsky was born in 1857 in the Russian Empire. Childhood illness left him partially deaf, limiting formal education and pushing him towards self-directed learning. In many ways, this isolation shaped his intellectual life. Removed from conventional academic pathways, he developed an unusual combination of mathematical rigor and visionary imagination. He studied physics, mechanics, astronomy, and engineering, not merely to understand the world, but to ask what humanity might become. That distinction mattered. Many scientists study reality as it exists. Tsiolkovsky studied reality as a framework for future civilization. He did not think only about rockets. He thought about destiny. In late 19th century Europe, the idea of space travel occupied an uneasy space between fiction and philosophy. Writers such as Jules Verne imagined voyages beyond Earth, but serious engineering remained primitive. Balloons had reached the skies. Artillery inspired fantastical launch ideas, yet no practical path to orbit existed. The atmosphere itself still represented an enormous barrier. Tsiolkovsky approached the problem differently. He treated spaceflight as a mathematical inevitability. If propulsion obeyed physical laws, then travel beyond Earth could be analysed rather than fantasized. This shift from imagination to calculation changed everything. It transformed space travel from dream into engineering discipline. His most famous contribution, the rocket equation, revealed a brutal truth that still governs astronautics. Velocity change depends on exhaust velocity and mass ratio. In simple terms, the equation quantified how much fuel a rocket needs to achieve a given speed. Elegant in form and merciless in implication, it exposed why reaching space was difficult and why interstellar travel would be vastly harder. The equation did something remarkable. It made hope more realistic and more terrifying, because Tsiolkovsky did not merely show that rockets could work, he showed exactly how punishing the physics would be. This dual legacy defines many transformative scientific insights. Knowledge empowers and humbles simultaneously. Tsiolkovsky gave humanity a path to the stars, while also revealing the mountain ahead. But equations alone do not explain why he matters so deeply to our story. His real significance lies in how far beyond rockets he thought. Tsiolkovsky believed humanity's future was inseparable from expansion into space. He understood something many of his contemporaries did not. A technological civilization confined permanently to one planet remains vulnerable. Planetary civilization faces finite resources, environmental instability, astronomical hazards, and long-term existential threats. Space offered not merely exploration, but civilizational resilience. Decades before the modern space age, he imagined orbital habitats, closed ecological systems, solar power in space, and long-duration human settlement beyond Earth. These ideas sound familiar now because later generations developed them further. But in his time, they bordered on radical speculation. He famously wrote words that still echo through space philosophy. Earth is the cradle of humanity, but one cannot remain in the cradle forever. That sentence became foundational. Why? Because it reframed exploration. Space was no longer just about discovery. It became about maturation. A child begins in a cradle because dependence is necessary. Growth eventually demands expansion. Tsiolkovsky suggested civilization works similarly. Earth nurtured humanity, but permanence within one planetary cradle might ultimately constrain survival and development. This idea remains emotionally powerful because it speaks to both ambition and vulnerability. The cradle protects. The cradle also limits. Yet Tsiolkovsky understood something subtler than expansion. Leaving the cradle is dangerous. Children stepping beyond safety face risk, uncertainty, and responsibility. The metaphor contained both promise and warning. Growth requires confronting environments that no longer forgive fragility. Space is precisely such an environment. The deeper Tsiolkovsky explored the mathematics of propulsion, the clearer the paradox became. Humanity could leave Earth, but leaving Earth did not solve vulnerability. It relocated vulnerability. A spacecraft is more fragile than a planet. An orbital habitat is more fragile than a biosphere. An interstellar vessel is more fragile still. This insight quietly foreshadowed the civilizational problems we have already encountered. A starship is not freedom from dependency. It is dependency intensified. Every system matters more. Every failure becomes more dangerous. Every design choice carries generational consequences. Tsiolkovsky may not have formalized these later concerns, but his work made them inevitable. Once rockets became mathematically real, deeper questions naturally followed. What kind of ships? What kind of habitats? What kind of societies? What kind of humans? These questions would shape the 20th century, and history moved faster than even Tsiolkovsky could have imagined. In 1903, the year the Wright brothers achieved powered flight, his writings on rocketry began reaching wider audiences. Aircraft had barely left the ground, yet within decades, humanity would build missiles, satellites, and orbital vehicles. What seemed speculative suddenly became industrial reality. The 20th century compressed technological change at extraordinary speed. Flight, radio, nuclear power, computing, spaceflight, moon landings. Humanity advanced from horse-drawn transport to lunar exploration within a single lifetime. This accelerated progress created dangerous optimism. Many began assuming that because progress had accelerated rapidly, it would continue accelerating indefinitely. If humans reached the moon in the 1960s, surely Mars would follow soon. Then orbital cities, then interstellar probes, then perhaps the stars. But Tsiolkovsky's mathematics never changed. Progress can accelerate. Physics remains indifferent. This tension defines the next phase of our story. Humanity entered the space age with extraordinary confidence. Rockets worked. Orbit became real. Lunar travel became real. For a moment, the stars felt closer than ever. Then another thinker helped humanity see the deeper truth, not through equations alone, through perspective, through scale, through a profound reframing of what the cosmos actually means for an intelligent civilization. His voice would shape how millions understood space, and more importantly, why space matters at all. His name was Carl Sagan, and he would force humanity to confront not only distance, but significance. By the time Carl Sagan emerged as one of the defining scientific voices of the 20th century, humanity had already crossed a threshold no previous civilization could have imagined. Machines built by human hands had left Earth. Humans had walked on the moon. Robotic probes had begun traversing the solar system. For the first time in history, space was no longer mythology or abstraction. It had become lived experience. And yet, something strange happened. The more humanity advanced technologically, the easier it became to misunderstand the deeper meaning of space exploration. Progress created confidence. Confidence created familiarity. Familiarity created illusion. Rockets launched often enough that many people began seeing space as simply another engineering frontier, an extension of aviation or telecommunications. Bigger rockets, better computers, more efficient propulsion. The conversation increasingly centered on capability. Sagan shifted that conversation. He asked a more difficult question, not how humanity reaches outward, but why? That question mattered, because capability alone does not sustain civilization-scale effort. Empires have built extraordinary infrastructure for short-term goals. Industries have transformed continents for profit. Militaries have mobilized planetary resources. But interstellar ambition requires something deeper than capability. It requires perspective. Sagan understood that cosmic perspective changes civilization psychologically. Space exploration was never only about destinations, it was about scale, and scale changes values. This became clear through one of the most famous images in scientific history. In 1990, at Sagan's urging, NASA commanded Voyager 1 to turn its camera back toward Earth from billions of kilometers away. By then, the probe had traveled beyond the outer planets. Earth occupied less than a pixel in the resulting image, suspended in a shaft of scattered sunlight. A tiny point, almost nothing. That image became known as the pale blue dot. Its power did not come from technical sophistication. It came from emotional collapse. Every human conflict, achievement, tragedy, empire, religion, revolution, discovery, and love story unfolded on that tiny point. Every king, every labourer, every child, every dream, every war, every philosophy, all contained within a barely visible fraction of a pixel. Sagan gave words to what the image implied. He reminded humanity that all our divisions, ambitions, and identities unfold within extraordinary fragility. The image did not diminish human importance. It reframed it. Smallness and significance are not opposites. This idea becomes crucial once we confront interstellar civilization, because cosmic distance produces two opposite psychological responses. The first is despair. We are too small, too fragile, too temporary. The stars are too far. The universe is too vast. Nothing meaningful can survive such scale. The second response is transformation. We are small. Therefore, cooperation matters more. Fragility matters more. Meaning matters more. Civilization matters more. Sagan consistently argued for the second response. He saw cosmic perspective not as nihilism, but as responsibility. This may be one of the most important philosophical insights in the story of space exploration. The universe does not care whether humanity survives. Therefore, humanity must care. That sentence becomes even more powerful when applied to distance. Interstellar distance is terrifying, partly because it strips away comforting illusions. On Earth, civilization often behaves as though time is abundant and resilience is automatic. Space destroys both assumptions. Cosmic perspective reveals how rare stable biospheres may be, how fragile technological civilization remains, and how easily progress could disappear. Sagan often emphasized another unsettling truth. The universe is old, very old. The observable universe is measured in billions of years. Stars formed and died long before Earth existed. Entire galactic histories unfolded before multicellular life emerged here. Humanity arrived astonishingly late in cosmic time. This creates one of the most profound questions in science. If intelligent civilizations can arise elsewhere, where are they? That question later became famous through the Fermi paradox, named after Enrico Fermi. The logic appears simple. The galaxy is ancient. There are vast numbers of stars. Many stars host planets. Given enough time, advanced civilizations should emerge. Some of those civilizations might expand. So why do we not see obvious evidence? Silence. That silence deeply disturbed many thinkers because it implied something troubling. Perhaps interstellar civilization is far harder than optimism suggests. Perhaps civilizations destroy themselves. Perhaps expansion stalls. Perhaps biology fails. Perhaps distance wins. Or perhaps advanced civilizations choose forms of existence we do not yet understand. Sagan approached this mystery with careful humility. He resisted easy answers. But he recognized something important. The silence itself is data, and that data forces civilization to confront uncomfortable possibilities. What if intelligence commonly emerges, but rarely survives long enough to spread? What if technological civilizations repeatedly fail during transitions involving energy ecology or governance? What if the hardest part of becoming interstellar is not propulsion, but surviving maturity? This idea connects directly to our story. We have already seen how interstellar travel escalates from engineering to biology to civilization. Sagan's perspective added another layer: civilizational wisdom. A species may become technologically powerful before becoming socially stable. That imbalance could be fatal. A civilization capable of atomic energy, planetary industry, artificial intelligence, or megastructure construction may still collapse if cooperation fails. In that sense, the stars test more than engineering. They test wisdom. This reframes interstellar distance in a startling way. Perhaps distance functions as a filter, not merely a physical barrier. A civilizational barrier. Only societies capable of extraordinary long-term coordination, resilience, patience, and cooperation may cross it. That possibility changes everything. The stars are not simply waiting for better engines, they may be waiting for better civilizations. This idea fascinated many thinkers after Sagan. Among them stood a physicist whose imagination repeatedly leapt beyond conventional constraints. He asked questions so large they often sounded like science fiction, yet his reasoning remained rigorous and deeply practical. If interstellar travel demands civilization-scale transformation, what form might such a civilization take? Would it still resemble ours? Or would advanced civilizations reorganize themselves around entirely different scales of energy and infrastructure? To explore that question, one scientist began thinking not in terms of ships, but in terms of stars themselves. His name was Freeman Dyson, and he was about to make humanity think far bigger than rockets. If Konstantin Tsiolkovsky taught humanity how to think mathematically about leaving Earth, and Carl Sagan taught humanity how to think philosophically about its place in the cosmos, then Freeman Dyson forced civilization to confront a more radical question. What if humanity had been thinking far too small? For most of the 20th century, interstellar ambition focused on vehicles, ships, probes, rockets, habitats. Even the most ambitious proposals usually centered on singular missions: build a spacecraft powerful enough to reach another star, solve propulsion, solve shielding, solve survival. Dyson questioned the framing itself. He understood something increasingly obvious from every equation we have encountered. Interstellar travel was not failing because engineers lacked imagination. It was failing because humanity kept trying to solve cosmic problems with planetary-scale infrastructure. But cosmic problems may demand cosmic-scale engineering. This shift in scale changed everything. Dyson was born in 1923 in Crowthorne and became one of the 20th century's most influential theoretical physicists. His work touched quantum theory, nuclear physics, engineering, mathematics, and long-range futures. Unlike many specialists, Dyson moved comfortably between rigorous physics and civilization-scale speculation. He possessed a rare ability to ask questions that sounded impossible, while remaining grounded in physical law. That ability produced one of the most influential ideas in future civilization thinking: not a spacecraft, a megastructure. In 1960, Dyson proposed a concept that later became known as the Dyson sphere, though the popular term oversimplified his original vision. He did not imagine a solid shell enclosing a star like a science fiction machine. Instead, he described something more plausible and in some ways more astonishing: a swarm of orbiting structures surrounding a star to capture significant fractions of its energy output. At first glance, this seems unrelated to interstellar travel. It is not. It may be central. To understand why, consider the scale of stellar energy. The Sun emits roughly 386 septillion watts of power. That number resists intuition so completely that ordinary language almost collapses. Human civilization uses only a tiny fraction of this energy. Even with industrial growth, our current planetary energy consumption remains negligible compared with total solar output. In simple terms, a star radiates far more usable energy than civilization currently captures. Dyson's insight was profound. Advanced civilizations might eventually expand outward, not merely for exploration, but for energy harvesting. As energy demand grows, civilizations may naturally construct orbital infrastructure to intercept larger portions of stellar output. Why does this matter for our story? Because every major interstellar obstacle keeps returning to the same bottleneck: energy. Propulsion demands energy. Shielding demands energy. Manufacturing demands energy. Life support demands energy. Computation demands energy. Civilizational redundancy demands energy. The farther humanity thinks, the more energy dominates the equation. Dyson recognized that interstellar civilization may be impossible without fundamentally different energy scales. This inspired another influential framework. In 1964, Soviet astronomer Nikolai Kardashev introduced a classification system for technological civilizations based on energy usage. His scale became famous because it translated civilizational maturity into measurable physics. A Type 1 civilization harnesses energy at planetary scale. A Type 2 civilization harnesses energy at stellar scale. A Type 3 civilization harnesses energy at galactic scale. Humanity does not yet qualify as Type 1. Pause there. We often imagine ourselves technologically advanced. By cosmic energy standards, we remain early, very early. This realization changes the emotional texture of interstellar travel. The problem may not be that star travel is impossible. The problem may be that humanity is attempting it during adolescence. A child cannot lift a mountain. That does not mean mountains are fundamentally unmovable. It means scale matters. Dyson's thinking reframed the challenge in civilizational terms. Instead of asking how today's civilization reaches the stars, we might ask, what future civilization becomes capable of such travel naturally? That question produces a startling answer. Interstellar travel may emerge only after civilization becomes vastly larger, more distributed, and more energy-rich than anything recognizable today. Orbital industry. Asteroid mining. Solar megastructures, autonomous manufacturing, distributed computation. Self-replicating industrial networks. Suddenly the Starship no longer appears as a lone heroic vehicle. It becomes the output of an enormous space-based civilization. This resolves some problems. Fuel becomes easier when energy is abundant. Manufacturing improves when industry expands off-world. Infrastructure becomes modular and redundant. But new questions appear. Bigger civilization means more complexity. More complexity means more coordination challenges. And perhaps most importantly, greater scale changes identity. Would a civilization spanning millions of orbital habitats still think like a planetary civilization? Would culture remain unified? Would politics remain centralized? Would humanity still describe a coherent collective? Dyson understood that large-scale engineering changes society structurally. Build enough infrastructure in space, and civilization ceases to be planet-bound. It becomes distributed across habitats, stations, colonies, and industrial networks. Distance begins fragmenting society long before interstellar travel begins. This insight returned us to a haunting theme. The deeper humanity expands, the harder unity becomes. Then Dyson pushed thinking even further. If energy abundance becomes extreme, perhaps civilization need not move biological humans across the stars at all. Perhaps smaller, smarter, more efficient systems go first. Machines. Automation. Self-replication. This possibility would later become central to interstellar strategy. But before that idea fully matured, one older concept regained attention, a concept both elegant and unsettling. If individuals cannot survive interstellar timescales, and if civilization struggles to remain unified, perhaps the solution is neither instantaneous travel nor machine-only exploration. Perhaps the ship itself must become civilization, a city in motion, a world between worlds, a habitat so large that generations live entire lives inside it, not waiting for civilization to survive the journey, carrying civilization as the journey. This idea had existed for decades, but now with growing awareness of energy scale and social complexity, it returned with new urgency. Humanity gave it a name, the Generation Ship, and it would force perhaps the hardest question yet. Not whether humans can reach the stars, but whether a civilization can remain human while crossing the abyss between them. By the time serious thinkers began returning to the idea of generation ships, the logic felt almost unavoidable. Every major path toward interstellar travel had collided with the same wall. Conventional rockets were too slow. Advanced propulsion demanded staggering energy. Human biology resisted long-duration space habitation. Civilizations drifted across generations, and the light barrier remained untouched. So a strange conclusion emerged. Perhaps the journey did not need to fit within a single lifetime. Perhaps that assumption had always been the mistake. What if humanity stopped trying to compress cosmic distance into human timescales and instead expanded human civilization into cosmic timescales? That idea sounds simple. Its consequences are profound. A generation ship is not merely a spacecraft with sleeping quarters. It is a closed civilization engineered for multi-generational survival. People launch knowing they will never arrive. Their children may never arrive. Their grandchildren may still be traveling. The ship itself becomes the only world most inhabitants will ever know. At first, this concept feels like a technical workaround. It is not. It is a civilizational transformation. The moment a mission spans generations, the meaning of travel changes completely. Traditional exploration follows a familiar logic. Depart, transit, arrive, return, or report. The mission remains anchored to a single historical moment. A generation ship breaks that structure. Departure and arrival become separated by centuries. Entire historical eras unfold during transit. Imagine a vessel leaving Earth in the year 2300. Humanity gathers to witness launch. Broadcasts span the planet. Political leaders speak of destiny. Families say goodbye to loved ones. Engineers celebrate the culmination of centuries of research. Religious leaders offer blessings. Artists compose music. Children watch history begin. The launch generation understands Earth intimately. They remember oceans, weather, cities, languages, music, cultural conflict, political debates. They carry living memory of the cradle. Now move forward 200 years. The people on board no longer remember Earth. They know Earth only through archives, stories, education, myth. This is where the generation ship becomes psychologically fascinating. Memory changes form over time. First-hand experience becomes recorded history. Recorded history becomes curated narrative. Narrative becomes culture. Culture becomes myth. Myth becomes identity. That progression matters because interstellar civilization depends on narrative continuity. The ship must preserve not only technical knowledge, but purpose. Why continue? Why sacrifice? Why maintain systems faithfully for centuries? Why care about a destination no living person has seen? These questions cannot be answered by engineering manuals. They require meaning. This is why generation ships force humanity into unprecedented design challenges. The physical architecture must support far more than survival. It must support civilization. Consider population size. A tiny crew creates dangerous genetic bottlenecks and social fragility. Too few individuals increase inbreeding risk, social rigidity, and psychological strain. Too many individuals dramatically increase habitat requirements, food demand, energy consumption, waste management complexity, and governance difficulty. There may be a minimum viable civilization size. No one knows exactly what that number is. Hundreds, thousands, tens of thousands. The answer depends on biology, genetics, automation, and culture. This uncertainty reveals something profound. A generation ship is not built like a vehicle. It is designed like an ecosystem. Food systems must recycle nutrients efficiently. Water must circulate in nearly closed loops. Agriculture must maintain soil or equivalent biological productivity. Pollinators may matter. Microbial ecology matters. Waste streams must become resources. Failure in one subsystem cascades through others. The ship begins to resemble a miniature biosphere. In effect, humanity attempts something extraordinary. Build a small artificial planet. This comparison is useful because Earth itself is not merely habitat. It is an enormously complex, self-regulating system shaped by billions of years of evolutionary feedback. Atmosphere, oceans, microbes, plants, animals, geology, and climate interact continuously. Humanity depends on these interactions in ways still not fully understood. A generation ship attempts to compress enough of that complexity into engineered systems. That alone is daunting. But physical ecology is only half the challenge. Social ecology may be harder. Every society develops status structures, prestige, power, class, identity groups, norms, conflicts, subcultures. A generation ship will be no exception. This raises unsettling possibilities. Suppose technical specialists become elite because they maintain life-critical systems. Engineers controlling reactors, agriculture, or oxygen production might accumulate disproportionate power. Governance could drift toward technocracy. Alternatively, charismatic ideological groups might dominate social narrative. Religious reinterpretations of the mission could emerge. Cultural factions might dispute destination priorities. None of this is speculative fantasy. It is historically normal human behavior. Closed environments do not erase human complexity. They intensify it. And then comes the most disturbing possibility: mission drift. Imagine the ship traveling successfully for 300 years. Systems function. Population remains stable. Culture evolves. Children grow up safe. Communities flourish. Art develops. Families thrive. A unique civilization emerges. Now ask a dangerous question. Why land? This question sounds absurd from Earth. It may feel entirely reasonable on board. If the ship functions as a stable world, arrival may introduce risk rather than salvation. Landing on an alien planet means environmental uncertainty, pathogen exposure, ecological mismatch, gravity adaptation, and societal disruption. future generations might rationally conclude that remaining aboard the ship is safer than colonization. This possibility changes everything. The mission may succeed technically while failing strategically. Arrival becomes optional. This deeply unsettled futurists because it exposed a paradox. A generation ship built to reach another world may eventually stop valuing worlds. The vessel becomes home. Home changes motivation. Motivation changes destiny. This may be the hardest problem in interstellar civilization. Not propulsion, not radiation, not food. Purpose. Can intention survive centuries, or does time inevitably rewrite civilization? For decades, generation ships appeared to be the most realistic path to the stars. They accepted physics rather than trying to defeat it. Instead of outrunning distance, they absorbed it into culture. But something changed. A different line of thinking emerged. It began not with sociology, ecology, or even engineering. It began with a dangerous question in theoretical physics. What if the problem was never speed? What if humanity had been trying to solve the wrong problem entirely? Because after generations of wrestling with distance, a radical possibility reappeared. Perhaps the answer was not to move faster through space. Perhaps the answer was to change space itself. And if that sounds impossible, it is because the next phase of our story enters territory where physics begins to feel almost philosophical. The breakthrough, if it existed at all, would not come from bigger ships. It would come from bending reality. For nearly the entire history of interstellar thought, one assumption remained unquestioned. If humanity wanted to reach another star, something physical had to travel across the intervening distance. A ship departs point A, crosses space, and arrives at point B. Every strategy we have explored so far accepted this framework. Better rockets, nuclear propulsion, generation ships, civilization-scale habitats. Different solutions, same geometry. Space stays fixed. The traveller moves. But what if that geometry itself was the mistake? This question sounds almost mystical at first, yet it emerged directly from modern physics. The deeper scientists studied gravity, motion, and space-time, the stranger reality appeared. Space was no longer understood as an empty stage where events simply occur. Instead, physics increasingly described space-time as something dynamic, something capable of stretching, curving, warping, and evolving. That shift changed everything, because once space becomes dynamic, a radical possibility emerges. Perhaps a civilization does not need to outrun distance. Perhaps it can manipulate distance. To understand why this possibility became so compelling, we need to revisit the light barrier from a different perspective. Earlier, the speed of light appeared as an absolute prison. Nothing with mass can accelerate through space-time faster than light. This seemed to doom practical interstellar travel. Even extraordinary propulsion left journeys painfully long. But there is a subtle detail hidden inside that statement. Physics forbids objects from moving through local space-time faster than light. It says something much less restrictive about space-time itself. This distinction matters because the universe already demonstrates something astonishing. Space can expand. During cosmic evolution, space-time itself changed shape on enormous scales. Distant galaxies recede from each other, not because they are flying conventionally through static space, but because space between them stretches. Pause there. The universe already performs something that feels faster than light, without violating local physics. That observation inspired an extraordinary question. Could an advanced civilization engineer local space-time distortion deliberately? If so, interstellar travel might look very different from traditional propulsion. Instead of accelerating a ship to impossible speeds, perhaps the ship remains locally stationary, while space in front contracts and space behind expands. The destination moves closer. The origin moves farther away. The ship rides a moving bubble of distorted space-time. Distance collapses. This idea remained mostly speculative until 1994, when Mexican physicist Miguel Alcubierre proposed a mathematical solution to equations derived from general relativity. His model described a theoretical space-time geometry now known as the Alcubierre drive. The idea electrified futurists, not because it produced a working engine, it did not, but because it showed something profound. Relativity itself did not completely forbid warp-like travel. The door was not fully closed. For the first time in decades, interstellar travel regained a different kind of hope. Not engineering hope, theoretical hope. A path existed within known physics equations, at least mathematically, where effective, faster-than-light travel might occur without locally violating Einstein's speed limit. A spacecraft inside a warp bubble would feel extraordinary in concept. Occupants might experience little acceleration. Locally, physics behaves normally. Yet externally, the bubble crosses vast distances at effective superluminal speeds. Imagine it. A silent vessel suspended inside distorted space-time. Stars ahead visually compress. Stars behind stretch into red-shifted shadows. Space itself becomes engine. No propellant plume, no explosive thrust, no roaring combustion, only geometry. The cinematic power of this idea explains why it captured public imagination so strongly. It felt like science fiction becoming mathematical possibility. But there was a problem. A devastating one. Energy. Again. The earliest calculations suggested warp geometry required forms of matter or energy, unlike anything humanity had ever observed in usable quantities. Specifically, the model demanded negative energy density, often described loosely as exotic matter. This is not ordinary fuel. It represents a highly unusual physical requirement involving stress-energy conditions rarely encountered in classical systems. In simple terms, warp travel demanded physics civilization could not yet access. Then came the scale of the requirement. Initial estimates were almost absurd. Depending on assumptions, creating a meaningful warp bubble appeared to require energy comparable to planetary masses. Not planetary power output. Planetary mass energy. Numbers so large they nearly erased practical optimism. For many, the dream collapsed immediately. The equations permitted the geometry. Reality denied the resources. Yet the story did not end there. Over time, researchers refined the mathematics. Some later analyses suggested the energy requirements might be reduced dramatically under different geometric assumptions. Reduced, however, is a dangerous word here. Even optimistic models still imply energy demands far beyond current civilization. The pattern felt painfully familiar. A breakthrough appears. Hope rises. Deeper analysis reveals a larger obstacle. Discovery. Complication. Again. And energy was not the only issue. Warp geometries raised troubling questions about stability, causality, and control. How does a ship create a bubble from inside if the required space-time structure must already exist? How does navigation work at effective superluminal travel? What happens at bubble boundaries where extreme energy gradients may appear? Could radiation accumulate catastrophically? Each question opened new uncertainty. Then an even stranger implication emerged. Some warp-like solutions seemed entangled with time paradoxes because once effective, faster-than-light travel enters relativity, causality becomes dangerous territory. Under certain conditions, superluminal paths can imply closed causal loops, where effect and cause become difficult to separate. In other words, the deeper humanity pushed warp theory, the more space-time itself began resisting simple interpretation. This led to an unsettling realization. The universe may permit extraordinary motion only by demanding extraordinary consequences. Reality does not hand out loopholes cheaply. Still, something important had changed. For the first time in our story, the obstacle of distance itself had been challenged directly. Not by brute force, by rethinking geometry. And once that conceptual barrier cracked, another idea returned from the edges of theoretical physics, one even older than warp drives, one even stranger. A structure not built by engines, but by topology. A shortcut through space-time, a tunnel connecting distant regions of the cosmos. Humanity gave it a name that sounded almost mythological, the wormhole. And if warp drives made distance negotiable, wormholes threatened to make distance almost irrelevant if they could exist. That final condition would prove enormous, because the next breakthrough would ask not whether we can bend space, but whether space-time itself can be folded. If space-time can bend, the next question becomes almost unavoidable. Can it connect distant regions directly, like a tunnel carved through the fabric of the universe? This idea did not begin as imagination. It emerged from mathematics. Long before interstellar travel became a serious engineering discussion, solutions to Einstein's equations hinted at something strange. Under extreme conditions, space-time could form bridges between distant points, not paths through space, shortcuts through it. These structures came to be known as wormholes. At their core, they are not objects in the traditional sense. They are geometries, a region of space-time folded in such a way that two distant locations become adjacent through a hidden connection. Instead of traveling across billions of kilometers, a traveler might step into one mouth and emerge somewhere else entirely. Instant distance collapse. But the word instant hides a deeper complication. A wormhole is not a stable doorway by default. Most theoretical solutions suggest extreme instability. The tunnel collapses before anything can traverse it. To remain open, it would require forms of matter or energy that behave in ways not yet observed in usable macroscopic systems. This is where the concept of exotic matter enters the story again, similar to warp drive discussions, but even more restrictive in practice. Still, the idea persists because it solves something no propulsion system can easily solve: distance without travel time. If a stable wormhole existed between Earth and another star system, interstellar distance would lose its meaning entirely. The journey would not require decades, centuries, or millennia. It would require only passage through geometry. But physics does not offer such shortcuts freely. The equations that allow wormholes also introduce constraints that feel almost protective. Stability is uncertain. Energy conditions are extreme. Causality becomes fragile. In some models, wormholes may allow time offsets between entrances, raising the possibility of paradoxical loops where cause and effect lose clear ordering. This is where interstellar travel stops being an engineering discipline and begins to resemble a negotiation with the structure of reality itself. At this stage in our story, humanity is no longer asking how to build better rockets. It is asking whether space-time can be persuaded to behave differently. And yet, even as wormholes remain speculative, they force a profound shift in thinking because they expose something unexpected. The greatest obstacle to interstellar travel may not be distance at all. It may be the assumption that distance is fixed. Once that assumption is challenged, every earlier limitation begins to look less absolute. If space-time can be reshaped, then the problem is no longer simply moving through the universe efficiently. The problem becomes engineering the universe itself into a more navigable form. But that possibility introduces an uncomfortable asymmetry. Warp drives and wormholes are not merely transportation technologies, they are civilization-scale interventions. To even attempt them, a civilization would need energy control far beyond planetary capability. It would require mastery over gravitational systems, vacuum energy, and space-time curvature on scales that dwarf anything humanity currently operates. Which brings us back to an earlier theme. Interstellar travel is not a ship problem. It is a civilization problem, and now it becomes something even larger, a physics problem embedded inside a civilizational evolution problem. Because if warp or wormhole technologies are ever possible, they will not appear in a world still struggling to unify planetary energy systems. They would require a civilization already operating at stellar or near-stellar scale. At that point, distance itself becomes a secondary concern. But until then, humanity remains trapped in a deeper reality. Even if space-time shortcuts exist mathematically, they may remain practically unreachable for a civilization at our stage of development, and so the paradox deepens. The solutions to interstellar distance, if they exist, may only become accessible after a civilization has already learned to live at interstellar scale. This creates a loop in the logic of progress. We need interstellar capability to build interstellar solutions, but we need interstellar solutions to achieve interstellar capability. And so attention shifts once again. If neither propulsion nor space-time geometry offers an immediate path, perhaps the answer lies in a different strategy entirely, one that does not attempt to move a single human across the stars, but instead redefines what is sent. The question becomes unsettlingly simple. If humans cannot cross the distance easily, could something else go first? Something smaller, something simpler, something that does not require biology at all. And once this question is asked, the story of interstellar distance enters a new phase, not about bending space, not about building generation ships, but about separating intelligence from the fragile limits of flesh. At some point in every civilization's confrontation with extreme distance, a quiet but irreversible shift occurs. The problem stops being about carrying life across space and becomes about carrying information, intelligence, and intention instead. Biology is heavy, fragile, slow to repair, and tightly bound to environmental constraints. Machines are not. This realization did not arrive as a sudden breakthrough. It emerged gradually, almost reluctantly, as engineers and physicists confronted the accumulated weight of every previous failure. Rockets were too slow. Nuclear propulsion was too complex and politically constrained. Generation ships were too socially fragile. Warp and wormholes remained mathematically intriguing but physically inaccessible. Every path that preserved human form across interstellar distance carried overwhelming cost. So a different strategy took shape. If humans could not go first, perhaps their extensions could. The idea sounds simple until its implications expand. A machine sent to another star is not merely a probe. It is a fragment of civilization operating independently across light years. It must carry sensing, computation, decision-making, and communication systems capable of functioning without repair from home. It must survive decades or centuries of transit and still perform meaningful scientific or exploratory work upon arrival. In early interplanetary missions, this was already partially true. The Voyager 1 launched by NASA operates far beyond any possibility of human intervention. It communicates across vast distances with signals so weak they require extraordinary sensitivity to detect. Yet even this iconic machine remains in cosmic terms close to home. Interstellar distance changes everything. Communication delays stretch into years. Repair is impossible. Adaptation must occur on board. Autonomy becomes essential rather than optional. This leads to a critical transition in design philosophy. A spacecraft intended for interstellar travel cannot behave like a remote-controlled instrument. It must behave like an evolving system. That idea introduces something new into our story. Artificial intelligence, not in the modern casual sense, but as a necessary structural component of interstellar engineering. A machine travelling for centuries cannot rely on static programming. It must respond to unknown conditions, unexpected damage, shifting mission priorities, and scientific opportunities that cannot be pre-scripted. It must, in a limited sense, decide. This does not mean consciousness in a human sense. It means adaptive autonomy, the ability to interpret data, modify behaviour, and maintain mission coherence without external guidance. Once this requirement is accepted, the interstellar probe stops being a tool. It becomes a system that persists through time. And once systems persist long enough, another phenomenon begins to matter: drift. Over decades, hardware degrades. Radiation accumulates. Subsystems age. Software evolves through patches and self-correction. Data storage shifts. Redundancy fails in unexpected places. Even the concept of original design intent becomes less meaningful. The machine that arrives is not identical to the machine that left. It is a descendant. This parallel with biological evolution is difficult to ignore. Biological organisms mutate over generations. Interstellar machines may also diverge over time, not through reproduction in a traditional sense, but through layered modification, adaptation, and environmental pressure. At this point, the boundary between machine and civilization begins to blur. A single probe may not be enough. If one machine succeeds, why not send many? If many succeed, why not allow them to build infrastructure? If infrastructure can be built autonomously, why not allow replication? This leads to one of the most powerful ideas in interstellar strategy: self-replication. A machine that can use local materials to construct copies of itself. The implications are immediate and overwhelming. A single probe could in principle become a network. A network could expand outward. Expansion could continue without further input from Earth. In theory, this creates a form of exponential spread across interstellar space. Not through human travel, but through machine propagation. At this point, distance begins to lose its traditional meaning. Instead of a single journey from point A to point B, interstellar space becomes a field of potential expansion nodes. But even this idea carries limitations. Self-replication requires resources. Resources require extraction. Extraction requires energy, precision, and environmental compatibility. Each new star system presents unknown chemical compositions, gravitational conditions, and structural hazards. In other words, autonomy must increase again. Machines must not only build copies, they must adapt to entirely new worlds. This raises a deeper question. If machines become sufficiently autonomous, sufficiently adaptive, and sufficiently persistent, what exactly are they? Are they tools? Are they explorers? Are they extensions of civilization? Or are they something closer to a new form of life, shaped not by biology, but by intention and design? This question is not philosophical abstraction, it is structural. Because as soon as machines can persist, replicate, and adapt across cosmic distances, they begin to resemble an alternative pathway for intelligence itself, one that does not depend on fragile biological constraints, one that may survive where biology cannot. But this introduces an unsettling asymmetry. Machines may be better suited for distance, but meaning, purpose, and experience remain tied to consciousness as we understand it. So humanity faces a division. Machines go first. Humans may or may not follow. And that separation raises a question that becomes increasingly difficult to avoid. If machine intelligence expands across the galaxy, while biological intelligence remains confined or delayed, what does humanity become in the long term? A species, a civilization, or something more fragmented? This is where the story of distance begins to shift from engineering towards something deeper, because once machines can travel where humans cannot, interstellar space stops being empty. It becomes inhabited, not necessarily by life in the traditional sense, but by activity, replication, computation, and structure evolving across billions of kilometers. And at that point, the question of distance transforms once again. It is no longer just about how far humans can go. It becomes about what kind of intelligence spreads when humans stop being the only actors in the cosmos. For most of this story, progress has followed a familiar rhythm. A limitation is discovered, a solution is proposed. The solution works partially but reveals deeper constraints. Then the cycle repeats, each time pushing humanity further from simple answers and closer to structural reality. By the time machine-based exploration entered serious discussion, interstellar travel no longer felt like a single problem waiting for a single solution. It had become a layered system of interconnected barriers: energy, distance, time, biology, civilization, and information. Each layer resisted simple resolution, and yet within this complexity something new began to emerge. Not a complete answer, but a credible opening. In the late 20th and early 21st centuries, attention shifted toward a radically different approach to interstellar travel. Instead of building massive ships carrying everything needed for centuries of survival, what if the payload itself was reduced to its absolute minimum? Not habitats, not crews, not even large machines, just information-bearing systems compressed into extreme miniaturization. This idea transformed the problem again. If mass is the enemy of acceleration, then reducing mass becomes the most direct way to increase achievable speed. A spacecraft no longer needs to be a vessel in the traditional sense. It can become a signal embedded in matter. This line of thinking led to concepts such as light sails, a thin reflective structure pushed, not by onboard fuel, but by external energy sources such as powerful ground or orbit-based lasers. Instead of carrying propellant, the craft carries only a sail and instrumentation. The propulsion system remains at home, separated from the spacecraft itself. This separation is critical. It breaks one of the most punishing constraints we have encountered repeatedly: the rocket equation's dependence on onboard fuel mass. By externalizing energy generation, acceleration becomes independent of carried propellant. One of the most widely discussed modern concepts in this category involves gram-scale probes propelled to significant fractions of light speed by intense laser arrays. In theory, fleets of these miniature spacecraft could be launched toward nearby stars, arriving within human timescales, for communication delays that, while still long, are no longer purely generational. At this scale, interstellar travel stops being about human survival during transit and becomes about data retrieval across time. This shift is subtle but profound. The question is no longer, can humans go? It becomes, can information arrive? This reframing produces something important in our narrative, a first credible break in the overwhelming barrier of distance. Not because distance disappears, but because its psychological weight changes. A journey of decades becomes imaginable when the traveller is not a living civilization, but a lightweight probe carrying sensors and memory. And for the first time since the beginning of our story, a pathway exists that does not immediately collapse under energy or biology constraints. But even here, realism returns quickly. Laser-driven sails face enormous engineering challenges. Beam precision must be maintained across astronomical distances. Interstellar dust becomes a serious hazard at high velocity. Even microscopic impacts carry destructive energy. Deceleration at the destination remains difficult, unless infrastructure already exists there, and communication back to Earth weakens dramatically with distance. So even this breakthrough is not a solution. It is a narrowing of impossibility. But its significance is not technical alone. It is psychological. For the first time, humanity can imagine a step beyond the solar system that does not require rewriting civilization biology or energy systems at planetary scale. Instead, it requires extreme but localized infrastructure. Massive, yes. But not civilization transforming in the same way as generation ships or warp fields. This distinction matters deeply in the arc of interstellar thinking, because throughout our journey, every earlier attempt forced civilization to become something fundamentally different in order to proceed. Generation ships required multi-century social stability. Nuclear pulse propulsion required geopolitical transformation. Warp concepts required physics beyond current access. Machine civilizations required redefining intelligence itself. Laser sail probes, by contrast, represent something more incremental, still extraordinary, but not existentially transformative at planetary scale. This creates a rare moment in our narrative, a partial convergence between imagination and feasibility. And yet, even as optimism rises, the true nature of interstellar distance remains unchanged. Because sending a gram-scale probe to another star is not the same as bridging interstellar civilization. It is a message, not a migration, a signal, not a presence, a moment of contact delayed by years or decades, not a shared lived experience. The star is still unimaginably far. Even at a fraction of light speed, Proxima Centauri remains a multi-year journey one way, with communication returning only after additional delay. The total loop between question and answer stretches into human generations, so even the breakthrough reveals a deeper truth. Distance may be partially crossed, but connection remains fundamentally fractured, and this fracture becomes the defining theme of everything that follows. Because once humanity accepts that interstellar travel may begin with machines, signals, and microprobes, rather than civilizations, a new question emerges. What happens when those probes begin to think for themselves? What happens when they begin to build? And what happens when the first wave of exploration does not stop at observation, but evolves into expansion? At that point, interstellar space stops being a static backdrop. It becomes a developing system. And the next stage of the story is no longer about reaching the stars. It is about what grows between them. Once the first wave of interstellar probes begins to function not as isolated instruments, but as persistent systems capable of adaptation, the universe changes in a subtle but irreversible way. Space, which once appeared as empty separation, begins to acquire structure. Not structure in the visual sense, but in the informational sense. Points of intelligence, delayed communication, autonomous decision-making, and self-sustaining activity begin to appear across vast distances. At this stage, distance no longer acts only as a barrier. It becomes a condition that reshapes civilization itself. Even before full-scale interstellar expansion, humanity already experienced fragments of this transformation within its own solar system. Communication delays to Mars, for example, force operational autonomy. A message sent from Earth may take between minutes and tens of minutes to arrive, depending on orbital alignment. Responses return only after similar delays. This introduces a new form of decision-making where immediate coordination is impossible. Systems must act independently within predefined boundaries. Now extend that principle outward to interstellar scales. A probe near Proxima Centauri does not merely experience delay, it experiences informational isolation. Every interaction with Earth becomes a historical exchange. Instructions are no longer instructions in real time. They are archival guidance. Every decision made locally is effectively irreversible from Earth's perspective until long after the fact. This creates a fundamental shift in the nature of control. Centralized civilization depends on synchrony. Laws, economics, scientific collaboration, cultural trends, and governance structures assume that participants exist within a shared temporal framework. Even when spread across continents, communication delays remain small enough to preserve coordination. But once distances extend to light years, synchrony collapses entirely. What replaces it is something more fragmented. Distributed autonomy. Each node of civilization, whether a probe, an outpost, or a self-expanding machine system, must operate as a partially independent entity. It receives guidance from its origin civilization, but evolves its behavior based on local conditions. Over time, divergence becomes inevitable. This raises a question that is both technical and philosophical. At what point does a distributed system stop being a single civilization? If Earth-originating systems spread across dozens, then hundreds of star systems, each adapting independently over centuries, the original unity begins to dissolve. Even if all systems share a common origin, shared memory becomes diluted by time delay. Shared experience becomes impossible. Shared culture becomes fragmented. Civilization becomes a network of delayed echoes. This is not a failure. It is a transformation. But it is a transformation that challenges many deeply held assumptions about identity. When we speak of humanity, we often assume continuity across space and time. But interstellar expansion introduces discontinuity as a structural feature. The further information must travel, the less simultaneous existence matters. Now consider how this affects technology. A machine operating near another star cannot depend on Earth for updates. It must develop local adaptation mechanisms. It must interpret unexpected environments. It must manage failure modes without external intervention. Over time, these systems become increasingly capable of independent evolution, and once evolution becomes possible, divergence begins. A probe designed on Earth may, after centuries of autonomous operation, no longer resemble its original design in any meaningful sense. Its software may have been modified repeatedly. Its hardware may have been partially reconstructed from local resources. Its objectives may have been refined through long-term environmental interaction. At that point, it is no longer merely a tool. It is a continuation, a branching extension of civilization. This introduces a second layer of fragmentation, not just spatial fragmentation, but conceptual fragmentation. Different branches of civilization may begin optimizing for different conditions. Some may prioritize exploration speed, others may prioritize stability, others may prioritize replication, others may prioritize data preservation over expansion. Over time, divergence is not only likely, it is structurally expected. This brings us back to a question that has been building throughout our entire journey. What does unity mean across interstellar distance? On Earth, unity is maintained through shared language, shared time, shared institutions, and shared memory. Even when conflict exists, resolution occurs within overlapping frameworks of understanding. But across light years, those overlaps shrink dramatically. A message sent from Earth to a distant system may arrive to a civilization that no longer interprets concepts in the same way. Language may have evolved, context may have shifted, priorities may have changed. Even the meaning of human may no longer be identical across branches of civilization. At this stage, interstellar distance becomes more than physical separation. It becomes semantic separation. Meaning itself stretches across space and time, and as meaning stretches, another phenomenon emerges. The possibility that civilization is no longer a single coherent entity, but a family of related systems evolving independently across the galaxy. Some branches may remain close to biological humanity. Others may drift toward machine-dominated systems. Others may become hybrids of computation biology and environmental integration. Each branch shaped by local conditions, local challenges, and local interpretations of survival. From a cosmic perspective, this is not fragmentation in a negative sense. It is diversification. But from a human perspective, it challenges the intuitive idea of a unified future. There may not be a single future for humanity. There may be many, spread across light years, evolving across millions of years, connected only by signals that arrive too late to coordinate, but just in time to remember. And this leads to a final unsettling thought. If intelligence spreads across the galaxy in this fragmented, delayed branching manner, then interstellar civilization may not look like expansion at all. It may look like memory propagation, each system remembering the origin, each branch carrying echoes of Earth, each distant node preserving a version of humanity that may no longer exist in any single place. At this scale, distance is no longer just an obstacle. It becomes the architecture of existence. And the final question begins to take shape. If civilization spreads across the stars, not as a unified entity, but as a slowly diverging network of memories, then what does it mean for any one branch to call itself the continuation of humanity? That question carries us into the final stage of our journey, where distance stops being a measurement of space and becomes a measurement of identity itself. By the time we reach the final layer of this story, distance no longer resembles anything we first imagined. It is not simply the empty space between stars. It is not even the time required to cross that space. It is something deeper, something that reshapes intelligence itself as it stretches outward into the universe. Because once civilization begins to spread across light years, something subtle but irreversible happens. The universe stops being a shared environment experienced in real time and becomes instead a structure of delayed connections, fragmented awareness, and slowly diverging histories. Each node of civilization exists in its own present, separated from every other by distances so vast that communication becomes less like conversation and more like archaeology. A message sent from Earth to a distant system is not received as dialogue. It is received as inheritance. A piece of history arriving late, a fragment of a civilization that may no longer exist in the same form by the time its echo is heard. And yet, despite this fragmentation, something remarkable persists. Continuity. Not physical continuity, not instantaneous unity, but informational continuity. The ability of patterns, ideas, and structures to survive across gaps that destroy physical synchrony. At this stage, we begin to understand that interstellar civilization is not defined by shared experience, but by shared origin. Every branch, every probe, every outpost carries within it a trace of the same beginning. Earth becomes less of a home in the geographical sense and more of a reference point in memory space, a fixed coordinate in the story of intelligence. But even that reference point becomes increasingly distant in a psychological sense, because as centuries turn into millennia, and millennia stretch further still, Earth itself may transition from lived reality into something closer to mythic origin. Not forgotten, but transformed, reinterpreted, preserved differently across branches that no longer communicate in real time. And so we arrive at a paradox that has been building beneath every section of this journey. Distance in its most extreme form does not separate places. It separates versions of reality. A civilization spread across interstellar space is not one civilization experiencing different locations. It is many civilizations experiencing different timelines, evolving under different constraints, gradually drifting apart in structure, culture, and understanding. Yet all of them remain connected by something invisible. Causality delayed, memory stretched, light itself carrying the only remaining bridge between them. Even at the speed of light, the universe refuses immediacy. Every signal is a fossil of intention, every image a preserved past, every transmission a delayed echo of thought that has already moved on. This is the final emotional weight of cosmic distance. Not emptiness, not isolation, but irreversibility. Once a message leaves, it does not return to the same world that sent it. Once a probe departs, it does not arrive in the same universe that launched it. Time ensures that no two regions of space ever truly share the same present. And so civilization spreads, not as a unified wave, but as a chain of delayed realities unfolding outward from a single origin point, each link slightly out of sync with the others, each carrying a different version of what it means to exist. In this sense, distance is not a physical obstacle waiting to be overcome. It is the fundamental condition under which cosmic intelligence evolves. It determines how civilizations fragment. It determines how meaning propagates. It determines how identity persists even when contact becomes impossible in practical terms. And perhaps most profoundly, it determines how intelligence learns to survive without ever being fully together again. So, we return to the question that has quietly guided this entire journey. How does humanity confront one of the greatest challenges in the universe? The answer is no longer a single technology, or a single breakthrough, or even a single path forward. Instead, it is a gradual realization that reaching the stars is not one event. It is a process of transformation so large that it reshapes what civilization is, what intelligence becomes, and what continuity means across the vast separation of space. Because in the end, the distances between stars are not terrifying simply because they are large. They are terrifying because they redefine everything that tries to cross them. And when we look up at the night sky now, we are no longer just seeing distant points of light. We are seeing the edges of futures that may never remain unified. We are seeing civilizations that may exist not as one, but as many. And we are seeing a universe where the greatest journey is not from one star to another, but from one version of humanity to all the others that distance will create. The universe is vast. Humanity is fragile. The challenge is immense, and yet the story is still being written.